But anyway, the next speaker is Daniel Meyerson, and you can see his lead slide on the screen. Over to you, Daniel.
Thanks. Yeah, I'm just gonna minimize the video here, Greg, so I don't see myself. So yeah, so thanks for allowing me to talk at this conference, which is in the cozy, in my own cozy home for a change. Yeah, so this is definitely a new experience for everyone. I've never done something like this before. Good. So I'm going to talk a little bit about microstate geometries and making them spark joy. So for those of you who don't know Marie Kondo, this might seem very weird. Why is there this woman here on my slide, and what is my title all about? So she is something of a personality, I guess, who cleans up. She has like a Netflix show and a book, and she cleans up things. And one of her things that she does is she tells you to, take each item that you own and ask yourself, does it spark joy? And if it doesn't, then you throw it away, right? So that's kind of the idea. And so we're going to declutter microstate geometries. In particular, I'm going to be talking about Superstrata using these two tools of holomorphy and dimensional reduction, right? And then hopefully this will convince you that this helps them spark joy or spark more joy if they already sparked joy before. Okay, so this was my way of roping you into my talk. So the talk's going to be mainly based on these two papers. So this paper that just came out sort of a month ago is about the dimensional reduction part, but I'm probably going to be speaking or using stuff from this paper the most, where I talk about the holomorphy part of the superstrata. Okay, so moving on to less fun things than Netflix shows about cleaning your house. So what am I going to talk about? I'm going to talk a little bit about, so I'm sort of introduce the scene. What's the general philosophy? What's the, what are we even talking about? What's the arena? The arena is going to be superstrata, basically. And then this will sort of naturally segue into the first topic that I want to talk about, which is going to be the holomorphic superstrata. So I'll tell you, what that means. It's basically going to be a clever choice of variables, a new clever choice of variables, which is going to allow us to write down some really cool stuff. And then the second thing that I'm going to talk about much more briefly is going to be why or how to dimensionally reduce some superstrata, which usually live in 6 dimensions or 10 dimensions to 3 dimensions, giving us a much easier theory to deal with, and so also give us something that's a lot easier to study. And then finally, sort of, if you don't care about superstrata at all, or at least not how to make them or what they do for you, then hopefully the thing that I can convince you to care about is the end goals, let's say, of these tools, which I will talk about as sort of the last part of my talk. Okay, so just to get started, the general, what's the general philosophy? What's the general arena that we're talking about, right? The general philosophy is we are not happy with black holes, right? We are not happy with black holes in general relativity. There's a bunch of problems with them. Sort of the most obvious problem is there's a singularity, which is this big black dot here. There's a singularity at the middle where we don't know what happens, right, when we hit it. And then there's a horizon that goes around the singularity that sort of cloaks it. But then there's also problems that have to do with the horizon, with the information paradox, et cetera. I'm not going to go into detail really of these problems. What I do want to say is, what is sort of the idea of the fuzzball proposal, of the microstate geometry proposal? It's basically we replace this singularity with a horizon around it by a bunch of quantum fuzz, right? And so here is a bunch of quantum fuzz for you. And so then the idea is that, if you are some kind of observer or you're some kind of particle that falls in, instead of falling in, going through the horizon and hitting the singularity, and then we don't know what happens, instead of that, we sort of hit the fuzz, we bounce around a little bit, and then we come back out, right? And so in particular, if you're just standing very far away from the structure, it looks like the black hole, but when you get close, you see all of this complicated structure. So this is the fuzz of the fuzzball, if you will. So this is the general philosophy. So in a very particular system, we understand pretty well, or we think we understand pretty well how this works in practice. And that's in the supersymmetric D1, D5 system, right? So two charges, we have some D1 branes and some D5 branes. The naive supergravity geometry is then not really a black hole, so to speak, but if we sort of squint and close our eyes a little bit, then you can sort of imagine that it's something like a precursor of a black hole or something like that. The reason why it's not really a black hole is because the horizon is sort of together with the singularity, so it's doesn't really have a finite horizon size. But nevertheless, what happens in these Luna and Mathur geometries is you have, instead of just this singular point, this is blown up to a string, basically. So we talk about the D1, D5 string sometimes. And so this string can be arbitrary, okay? And that's a very important point. This string is, some arbitrary function, so it's some arbitrary closed loop. And so you can write that as some arbitrary vector of a function of one variable, right? And so this is the first time to be saying these words. So functions of one variable, right, give you some kind of one-dimensional profile, and that's what these D1, D5 geometries are characterized by. So in particular, if you want to say, well, I want to know all the microstates and I want to then count them, that's something you can do. You can do some kind of semi-classical quantization, which leads to some symplectic form. Not really going to go into details here, but the point is this is something you can do in supergravity. You can say, I want a notion of quantizing the number of curves, the number of microstates. And once I've quantized them, I can count them. And lo and behold, sort of one of the big triumphs of this whole paradigm is that, when you count the number of curves in this way, you get a very nice agreement with what you expect the number of states to be in the D1, D5 system. So I'm not going to be talking about, the prefactor and, which modes are you turning on or off. That's sort of not, that's sort of beside the point for the moment. The point is just, you have a bunch of these microstates and you can count them using some semi-classical quantization. And, maybe you expect this to correspond to all of the states or some finite fraction of the states, or maybe not. And in this case, there's a clear match that you do expect them to correspond to the right number of states in a sense. Now, moving on to, so this was sort of the two-charge system, right? So as I said here, we have this two-charge system, which is just this one-dimensional curve. When we want to upgrade this, let's say, to a three-charge system, so this is what happens here. What happens when we add an extra charge momentum. So the D1 and D5 branes, they share a common direction, and so we can add some momentum wave along, some null momentum wave along this direction, giving us a third charge. And so this black hole with three charges, still supersymmetric. Everything we're going to be doing here is supersymmetric pretty much. This now has a finite horizon. So this is a bona fide black hole, and so we're really happy. We're much happier with this than with the D1, D5 system, let's say. And so in the same vein, we hope or we expect that we can construct some kind of superstrata, which would be which would correspond to blowing up this singularity, giving some the microstates of this black hole. And so typically what's done very heuristically is you can consider a D1, D5 system, and what we typically do when we want to consider superstrata is we consider the circular, so this is a circle, yeah, with circular geometry, the circular geometry up here of the D1, D5 system, and then we imagine sort of adding momentum on top of that, right? So we add momentum on top of that. And what my horrible drawing is trying to teach you is that we're not going to have just a simple curve anymore. We're going to have a complicated surface or strata. And so in particular, this superstrata should be, this superstrata should be not a function of one variable anymore, right? And so to see how many variables it is, it takes a little bit of work, but there are arguments that show that we should be looking for functions of three variables, right? So arbitrary functions of three variables that parameterize this surface, this strata, if you will, that corresponds to a microstate of the D1, D5P system. And so you might imagine, this is sort of a side note, that you can do a similar kind of counting as you can do for the D1, D5 system. You count the number of surfaces, right? You count the number of these functions of three variables that you can construct. And ask yourself, does this correspond to the entropy of the black hole, right? If you take the log of it. And so Masaki Shigemori has a nice paper counting the superstrata that we can, in principle, construct in supergravity, showing that it is, parametrically not enough to account for the entropy. Masaki and I have a paper that we're trying to write showing that we can do this also in supergravity directly. But in principle, you're still missing some states, and so then you can either be pessimistic or optimistic, and what realists will say, I'll leave in the middle of it. If you're pessimistic, you'll say, well, that's because supergravity is never going to be able to account for all of the superstrata because there's just not enough supergravity modes. You need to turn on inherently stringy modes to be able to have enough states, have enough structure, to have enough surfaces to count. Certainly possible. Or, if you're optimistic, you might say, well, it's just something in supergravity that we don't understand yet, that we need to turn on, that we can introduce still some extra structure that we haven't found in the equations, in the solutions. So I'm going to be sort of agnostic, since that's not really what I'm going to focus on. But that's sort of let's say that's the setup, right? The scenario that we're talking about. This sort of segueing into the description of superstrata. So again, I'm just sort of repeating what I said before, but a D1, D5 microstate, if you remember, is a curve, or so an arbitrary function of one variable. Of course, any kind of closed loop I can decompose into Fourier coefficients, and so any kind of periodic function I can decompose into Fourier coefficients, and so the function is completely determined by the Fourier coefficients, and vice versa. Why do I do this? Well, in the D1, D5P system, we can also imagine the same thing, right? So I said, we have functions of 3 variables. So that means that each Fourier mode should be basically having three indices, right? So one Fourier mode is going to look like this. And so the point is that, the superstrata that we know are mainly the ones where we only turn on one of these Fourier modes, right? So you give me one K, M, and N, and then, some value for this B, and then, I can give you a geometry, right? Something like that. And so the reason why, one Fourier mode is possible, but more than one Fourier mode is hard, is because these guys interfere in all kinds of places, and you need to, so as soon as you have more than one mode, they're going to interfere with each other in various places that you need to either cancel or take into account, or, gravity in general is a nonlinear thing. And so whenever you have 2 things instead of 1, then, it's not just 1 plus 1, right? Everybody knows this. So in principle, we know how to solve this due to some work by Pierre and Nick from last year. But in practice, superposing more than one mode is still a really hard problem. And I think one of the main issues here is that let's say before our holomorphy paper, we didn't really have an idea of what the variables were that we're trying to look for. We're trying to look for arbitrary functions, which we don't know what they are, of 3 variables, but we don't know what the variables are either, right? And so that kind of makes things hard if you don't know what the functions are or what the variables are that the functions should be functions of. And so this was sort of the state of the art before. Now, apologies for hitting you over the head with some equations, but this is just for people who are interested in understanding a little bit more in detail. These looks like a lot of equations on a slide, but I'm going to just try to guide you through it a little bit. So we're working in 6 dimensions, and so we have some metric, we have some 3 forms, we have 3 forms, and we have 2 scalars, which I'm not really going to talk about. And so the general form of the metric is something like this, right? So there's a 4D base. This is a spatial base. The 4D spatial base is in blue. And then we have 2 null coordinates on top of that, right? So 4 plus 2, 6 dimensions. Everything is going to depend on all of the 4D base coordinates in principle and on the null coordinate v. And so BPS, the BPS conditions tell you that, you have to pick one of these null coordinates that is a killing vector, and so nothing is going to depend on you. So everything can depend on everything else though. So that's five variables that we can depend on. Okay, so you need to tell me, to completely specify this solution, you need to specify all of these functions. So how do we do this? Well, first of all, we're going to start with the 4D base, and we're just going to fix this to be flat space, flat R4, right? So this 4D base, this is like step 0 in solving the equations, let's say. The 4D base is fixed, and the one form beta, which you see appearing here, this is also fixed. Okay, so the blue things are fixed, and we're not going to touch them. Then there's what's called the first layer of equations, and these are linear. So linear meaning, in principle, I can just integrate them and solve them, right? These are linear ordinary differential, or linear differential equations in a general sense. So these linear equations are going to determine for me these 3 pairs. And so what are these guys? The z's, for our purposes, are the things that appear here in the warp factor. So this warp factor curly p, you see appearing as sort of an overall factor here and also here. And then these thetas, I'm gonna talk about less, but these are related to what appears in the 3 forms, right? These are some 2 forms, these thetas actually. Okay. So once you've solved these linear equations for the z guys and the theta guys, then you have another layer, the second layer, it's called, of again linear equations that determine the leftovers, and the leftovers being, in this case, the 2 metric functions, the metric function f and the one form omega. Okay, so let me sort of repeat that in a little bit more detail, giving you also how this works for a single mode. So again, the 0th step, or 0th layer, if you will, is this 4D base that we fix, right, we fix it to be flat space. And then we go and we say, okay, I want to fix these 3 pairs of functions, and we single out one of them and say this guy is going to be trivial. Okay, so we don't even have to think about this anymore. The blue guy is trivial. We don't think about this guy anymore. The guys that are red are the guys that we're going to let depend on our modes, right, on these Fourier coefficients. And so in particular, Z4, the thing I want you to take away from all this complicated math is there's some thing, Z4, that is proportional to a single mode, like the Fourier coefficient of a single mode, right? Okay. So this completely determines my Z4. And so I've introduced now my Fourier coefficient. Something called coiffeuring has to then happen and fixes completely my Z1. So what is coiffeuring? Well, like I said, anything in supergravity interferes with everything else. And so in particular, even a single mode like this guy here interferes with itself, interferes with itself and produces modes that are of higher frequency. So let's say, 2K, 2M, 2N. And this high frequency thing takes a lot of work to see this, but this high frequency stuff is bad. And so we want to cancel that. This needs to go away, or we're going to have some highly singular solutions. And the way to cancel it is basically saying that this guy needs to be the square of the single mode. Okay, so this cancels the high frequency part of interference between modes. Okay, now this thing, this is just a one single mode thing. Generalizing this is easy. So here for Z4, you just say, okay, well, if I have more than one mode, I just have like a sum over modes. For this, it's a little bit harder, right? Because you need to take into account all possible pairs of modes, right? So you don't just have the square of the single modes, but you also have, if you have mode 1 and mode 2, they can interact with each other, and you take that stuff into account. But in principle, this is sort of easy, right? We can do this. This is not hard. It's just a bit of a drag. The second layer is where things get mainly where things get hard, where you want to solve for these omega and f things. Okay, and that's sort of I would say this is the biggest stumbling block when you're trying to actually find solutions. Is to find a way to integrate your differential equations to find these metric functions. Okay, now this was all done in the coordinates that I was talking about before. So in particular, if you remember the blue coordinates here are theta and 2 phi's. These guys are the coordinates of the 4D base. And then there was this one null coordinate, which we can depend on, which is this purple guy. And so things were hard in these coordinates, but what we're going to do, and so from the point of view of what I've said so far, this is sort of arbitrary. But of course, this is well motivated by explicit examples. We introduce these 3 new complex coordinates instead of these 5 real coordinates. right? And so basically I just introduced some combination of all of these guys. So again, I don't want you to take away from this the exact structure of this. What I want you to take away is that these complex coordinates mix the base and the null coordinate, right? So the base coordinates are the blue coordinates, and the purple coordinate is one of the null coordinates on top of that base. And so these coordinates really mix explicitly these coordinates. And so from the point of view of the supersymmetry equations, which really sort of single out the base as something special, this may seem surprising because the base is really this object which you put on top. You put these null coordinates and this null dependence. But from the point of view of these superstrata solutions, it seems like this is really the natural way to go. So just to
Daniel?
Yes.
Are we talking about BPS solutions in 1,0 supergravity or 1/2 BPS in 2,2?
Yes. So we're talking about, if you want to think about the full string theory, we're talking about 1/8 BPS solutions, right? So these are D1D5P 3 charge guys, so they break up down to 1/8. And so they live in a, if you want to go down to 6 dimensions, they'll live in, okay, depending on what you mean by minimal supergravity. So minimal supergravity in 6 dimensions has the metric and an anti-self-dual tensor. So where these guys live in is going to be a 6-dimensional theory with a metric, 2 scalars, and 3 tensor forms which are related by a self-duality condition. So basically it's minimal supergravity plus 2 tensor multiplets, if you will. Is that your question?
Thank you.
Sure. So I'll also come back to that in a bit. When we talk about the reduction, I'll show you the exact field content. But yeah, so this is minimal supergravity plus a few extra tensor multiplets, basically, if you want to keep it like that. So the 1,0, yeah. So right. So the in particular, let me just finish that thought. The D1D5 system itself, if you want to write down like the Luna Mathur geometries, they live in the minimal supergravity. But if you want to turn on the extra modes, the new modes that you need for the superstrata, so you want to turn on the momentum modes, you need to add this extra tensor multiplet in minimal supergravity. Okay. Good. So right. So okay. So we've introduced these complex coordinates, and from the point of view of supersymmetry, it's sort of mysterious why you would do this. Nevertheless, what happens is in these complex coordinates, your Fourier coefficients and the general structure of your equations gives you things that look very nice. So what do I mean by that? What I mean by that is what you end up having in your first layer. So remember, your first layer is sort of determined by this Z4 function, which is which is linear in these Fourier coefficients. The general form of this guy is going to be some sum over these Fourier coefficients times powers of these complex coordinates. So your arbitrary function is, I mean, this is sort of a conjecture. Your arbitrary function of 3 variables is going to be precisely this function, which is given by the Fourier this expansion here, is going to be precisely an arbitrary function of these 3 complex coordinates. Okay, it's going to be an arbitrary holomorphic function of these three complex coordinates. And not only is this a very sort of satisfactory way to package our modes, it's also, oh, sorry, so I should say there should also be a second arbitrary function here for the supercharged modes, but I'm not really going to talk about those. Just wanted to mention that for people who are familiar with the supercharged modes as well. Right, so not only does this give us a convenient way of packaging things, but it also makes solving the various consistency conditions, et cetera, much easier. So for example, the coiffeuring, which is, you know, I need to make sure that all of the high frequency interference between pairs of Fourier coefficients gets canceled, right? All of this high frequency stuff gets canceled. Well, this was some complicated combination of all of the pairs of Fourier coefficients. But if you rewrite this in terms of these arbitrary functions, or of this arbitrary function, it just becomes the square of this arbitrary function. Okay, and that's very, I mean, it seems almost trivial when I say it, but that helps you a lot when you're looking for solutions, right? And so using this new formalism, we were able to find a whole bunch of solutions that depend on arbitrary functions. I'm not going to talk about a lot of them in detail. I'm going to talk about one of them more than others, which is the first one here. But there's two things I want to point out in this list. So this is the list of solutions that we found, right? So there's two things I want to point out about this list. The first is that we have arbitrary functional dependence on one complex variable, right? So all of these guys, you'll see there's either one function or two functions like this guy worth of arbitrary dependence on one variable. Okay, so and this is new, right? This is something that was not really, people were not really successful at writing down because it was just a big mess. And you can kind of understand that this is true because as soon as you have something like, this squared, and then you want to expand that into all of the different Fourier coefficients, it's going to be a big mess, right? Okay, so that's one thing I wanted to say. We have some new arbitrary functional dependence. The second thing I want to say is you'll notice that there's no functional dependence on, or no arbitrary functions of two or more variables, right? Even though we expect that the most arbitrary superstrata will be some arbitrary function of three variables. And that's definitely where we hit a wall, right? So we're able to find, for example, if you look at the 1,0n, we're able to find some arbitrary functional dependence here of on psi, but fixing the chi dependence. The chi gives you basically the one, and so the ends, you can have as many ends as you want. And that's basically telling you you have an arbitrary function here. If you sort of look at the reverse of this, which would be k0n, so you have as many k's as you want, which corresponds to a function of chi, an arbitrary function of chi, but you fix the n to be 1, then you get this guy. And then you can ask yourself, well, can't I sort of put the two together? And that seems to be very hard, right? So the best we've been able to do is to give as many k's as you want, but fix n to be something higher than 1. And then you get, well, your basic function is going to be something a little bit more complicated, but the actual solution itself is also going to be much more complicated. Okay, so we've sort of hit a wall in that we don't really know how to go further than functions of one variable at the moment. Okay, so this is sort of just to say.
Daniel, can I ask a question?
Yes.
So, like in principle, how does the strategy go? So to find these functional forms, you just take the known modes for known examples, and you do this sum explicitly and express it in some fashion, like literally example by example.
Yeah. So okay, so you're asking like how do you find these solutions, basically, yeah. Right? Yeah. Okay. So in our so there's two ways to do this, which you can say is maybe the old-fashioned way or the slightly newer fashioned way. I don't know. But the old-fashioned way would be to look at a single mode solution first, and so we understand that solution very well. Then to generalize this to a double mode, right? So to two modes, but still not using necessarily the complex coordinates, and then understanding what the solution has to be for this double mode, and then generalizing this or trying to guess sort of a generalization to all possible multi-modes, right? So in particular, you would take, for this one, you would take 1, 0, n1 and 1, 0, n2, and you would try to find this solution. And then once you have this double mode solution, you can sort of see this holomorphic structure of, where do I put these f's? Where do I put f prime? Where do I maybe put, f squared or something like that? You can see that appearing. If this sounds like more of an art than a science, I think that's definitely true. But this is sort of in practice how we found a lot of these solutions. Another way you can do is, you can just start by writing down all of the supersymmetry equations, et cetera, in the holomorphic formalism. And so this we give this in our paper, and then doing this and then having a little bit of insight from how these things should look like. You can imagine just giving in, for example, if you want to find the 1, 0, n guys, you have this holomorphic formalism, you enter in this function, and then you solve for the metric functions, et cetera. Okay, and then that'll give you a solution. So that's sort of the more new way of doing things. I think in any way, you're always going to, like, there's no, just to be clear, there's no way that you can, like, at this point, program your computer to just spit out the answer, right? It's not like it's just simple integration. There's some particular solutions to differential equations that you need to find on a sort of a case-by-case basis. This is the hard part of
Right.
finding these solutions. So
just like when you start
Yes.
with two modes, say, and you guess this
Mhm.
functional form, you go check it with the BPS equations and the supersymmetry equations, and like.
Well, I mean, the BPS equations give you what the double mode would be, and then you can sort of try to generalize this immediately to a general multimode solution, and then plug in
Right.
what your guess is and see if that
Conform your
works,
guess.
something like
Okay.
that, roughly speaking.
Okay.
Yeah.
Yeah. Thanks.
I can. Yeah.
May I ask a simpler question?
Yes. Yes.
I missed why the exponents of chi, eta, and psi in the second line were positive. We were talking about holomorphy. So
Yes. Yes, I'm talking about holomorphy. Are you talking about? Oh, you're talking about here, over here. So, yes, I am talking about holomorphy, and so yes, they need to be positive. Yes, I didn't talk about this really, but this, but yeah. So for example, M has an upper bound of K, so you can't make M bigger than K, and this feeds directly into that. This is always going to be a positive exponent. Was that your question?
it's just about spherical harmonics, or because harmonic analysis on a circle would have exponents that would be both positive and negative.
Yeah, so it's sort of hard. I don't know how to answer that question very easily. How you can sort of very easily see that you need to have positive exponents. From the CFT, like if you know, because obviously we know what the CFT dual is of these guys, and so then it's obvious that only plugging in positive numbers makes sense, because these are like powers of operators that you're applying to a CFT state. So, but other than that, just directly from the supergravity, I mean, I guess you could try to plug in negative exponents and then see what happens. Yeah, I'm not. Maybe one of the Superstrata people has a better.
I think if I remember right,
this probably. Yes.
If I remember rightly, what happens is that it is indeed exactly as Ben was saying. It's spherical harmonics, but BPSness puts positivity constraints, I think, on the particular modes, so that the M's are always positive and go from 0 to K. If you start putting the other, so you've got two options. You either do non-BPS and then K's and M's, or take any old value you like.
Right.
But if you actually insist on it being BPS and you put in M's being bigger than K, there's a solution, but it's singular. So
Thank you.
All right, thanks. Good. So, okay. So, yeah, if there are any other questions, please just continue interrupting. That's fine. I'll pause if I remember, later for questions. Please do keep interrupting. So I want to focus a little bit more on. I'm going to be focusing mostly on this guy. So this let's say this is sort of our prototype solution, which has some arbitrary functional dependence. And this is the 10n guy, right? So I'll be calling it the 10n guy. And this is what you should have in mind. So once you've written down the solution, so finding the solution is one thing, right? So if you write down your arbitrary function, you go through this procedure of solving the BPS equations layer by layer, you find some solution. You're not quite done yet, because you need to put in some regularity conditions. You need to make sure that everything's regular. Just like Nick was saying, you don't want singular solutions, especially not if you're talking about microstate geometries, right? So in particular, you need to fix the UV. You need to make sure that everything is asymptotically ADS3 across S3. And in the IR, you need to make sure that that there's nothing singular going on at the supertube locus or origin, something like that. So there's some UV and some IR stuff that you need to take care of. Now, this all sort of corresponds to saying that your arbitrary holomorphic function just needs to satisfy some condition. We'll see this explicitly in the first few slides. It doesn't really matter, but the point is that its modulus squared integrated over the compact circle at infinity, right? So it's about a bit of a mouthful, but you can see it here in the equation. This thing has to be fixed in terms of the D1 and D5 charges, okay? And a further condition that you want is that there's, of course, no CTCs. So no closed time light curves, right? Because that would be very bad. Now, it turns out that when you have a multi-mode solution in general, it's actually a very subtle question whether you have CTCs or not. And in particular, you know, a closed time-like curve, the name says it itself, it's closed, it's a closed loop, right? And so if we have a closed time-like curve, this means that it's first of all closed, but it's time-like everywhere along the loop. Okay, so if there's no CTCs, then this is something you can prove by looking at the metric and studying it a bit. To have no CTCs, you need to demand that for some value along this loop, along every loop, right, any loop that you can think of, for some value or some point along this loop, this inequality is true. Okay. Now, if you think about it, this is this integral that I was talking about over here. This is an integral of the modulus squared at infinity. So at r is infinity. And this is just the modulus squared of wherever you are, your point on your loop. Okay. And so if you just think about, for example, the loop that is exactly at r is infinity, then this inequality is definitely not always going to be true, right? Unless you have some very trivial system. Because if your modulus, you know, fluctuates up and down, this is basically this is the average of the modulus, and so there will be points where it's going to be larger than the average, and there will points be lower than the average. But we don't need it to be. We don't need this to be true everywhere. We don't need every closed loop to be space-like everywhere. We just need it to be space-like somewhere, so that it's not a closed time-like everywhere loop. And so this sort of corresponds to this inequality here, which is an inequality in complex analysis, basically, right? And so for the 1,0n, we were successful at actually proving this using just complex analysis. The equivalent statement, the analogous statement for other solutions in our big compendium of solutions are slightly different, but they're all, you know, complex analysis statements. Some of them we just don't know how to prove, but we still expect them to be true. So if someone's really good at complex analysis, they can go to our paper and see if they can prove these things using complex analysis. Okay, so what I'd like to do, just very briefly, I know that this is horrible for talks, but you know, I just want to give you a little bit of an overview of what the solution looks like, right? So again, I'm looking at my prototype 1,0n solution here, which is completely characterized by this function f, holomorphic function f. If you remember from before, I have my 6D metric with, you know, there's a warp factor p, and there's the other unknown things, right? Because remember, the 4D base was fixed and this one form beta was fixed. The other unknowns are this one form omega and this function f. And so without staring at it too long, all I want to show you is, look, this is my warp factor. It's a very simple function of f, or in particular of the modulus of f. Look, this is my curly f. It's a very simple function of the modulus. And then this is the modulus evaluated at the boundary, so at r is infinity. It's a very simple function here of f squared. The one for an omega looks a little bit more complicated, but you know, again, it's sort of very simple in terms of this modulus squared, right? In terms of the arbitrary function. And this c is exactly what I was talking about before, where where this integral of the modulus squared at infinity, so that's exactly what this thing is here, is fixed in terms of the d1 and d5 charges of the system. Okay, so you know, forget all about this and just remember, oh, it's a lot easier when we have these holomorphic functions, if you will. Turning away from equations, giving you a little bit more sort of a geometric insight, hopefully, onto how these geometries look like, right? What do they really physically look like? Okay, so if we would have had, so again, this is a 6D geometry, but they sort of factorize asymptotically as a ADS3 cross S3. If it would have been the BMPV black hole itself, so the black hole that we're talking about in terms of microstates, if it's a black hole itself, this is just BTZ cross S3, right? So then it would just be the ADS boundary, and then you would have a BTZ throat, and then at some point here, you would have the BTZ horizon, okay? And so I'm gonna forget about this S3 for a minute. We'll talk a little bit more about this S3, obviously, in the reduction section, right? So focusing on this ADS3, if we would have just have the black hole, it's ADS boundary, and then BTZ, and then some horizon. Okay, if we have a microstate, the horizon is, of course, completely gone, right? We have, instead of the horizon, we have a smooth cap. So the space-time just ends at some radius here, okay? And this is of course the violent departure from horizon physics, right? We have structure, we have a cap instead of a horizon. And so the closer we are to this cap, the more structure we're going to see. And the further away, the more it looks like BTZ. And in particular, at the boundary, we just have the ADS3 boundary like we always do, with corrections that come into there. Now, what I want to, so the picture again of the microstate is that it looks like BTZ, but there's some extra structure on top of that, right? And so the structure here is the cap, which is just a smooth cap without any time dependence or V dependence. And then there's a BTZ-like throat. So what do I mean by that? It looks like the BTZ geometries, but there's also some time dependence. There's wiggles, okay? So this is what I like to call wiggles. And these wiggles are a function of V. So V again is like some null direction. So it's like T plus Y, where Y is this compact circle. And so these wiggles are really, V-dependent waves, V-dependence on top of this BTZ throat, right? So we really see some time dependence in the geometry at finite distance away from the cap. And in particular, if you look at the ADS boundary, the first corrections to just pure ADS come at 1 over r squared. If this were, let's say, the BTZ black hole, this 1 over r squared correction would just give you the charge, right? The momentum charge or the mass of the BTZ black hole. For this microstate, this is also true when you integrate it over the compact direction, which you always need to do to get a charge, but it's also something that depends on V. So in particular, when you move around the circle, you might have some charge that is very big on one spot of V, right? One value of V, and then somewhere else, you might have much less charge, much less momentum charge. So you can localize, in a sense, these momentum waves. So let me make this a little bit more precise. So I'm going to plot here
Daniel, maybe
yes, please.
A question before that. So
yes.
This time dependence, how in the metric, how should we think about it? Like that is intrinsically there in the solution, or is it like, I don't know, leftover of formation, or should I just be thinking it's just there? That's life.
Do you mean in the sense of like the solution, or do you mean like?
Yeah. I mean, like, yeah.
Because from the point of view of the solution, it's just another coordinate that we depend on, right? And so the time dependence is so we don't really depend explicitly on time. We depend on this null coordinate, which is like T plus Y, right? So it's always going to be time dependence that's like a wave traveling around.
So in a way, I should be thinking about it like the momentum wave is sort of.
Yes, it's exactly that. It's exactly.
Okay, so it's nothing like dynamical, like formation. Okay.
No. I mean, we're not talking about anything. I mean, we're in BPS, so there's no dynamics anyway, in a sense, right? So, but no. So it's really just this momentum wave that's traveling in the V direction. Yes. Right. Good. So what I want to show here is this is a plot, sort of a density plot of roughly speaking, this is the component of the metric along the compact direction. So the GYY, if Y is the compact direction. And so, I mean, the exact form of it is not really important. It's minus the modulus squared of this function, right? So that's sort of what I'm getting at. If you have a single mode, what I want to point out is, I should also point out what are the values here. So the origin, right, the ADS origin or the cap is always going to be the center here with r equals to 0, which corresponds to the complex coordinate equals to 0. That's always going to be the origin. The boundary of the disk is exactly where the modulus of this coordinate psi is 1, and so this corresponds to the ADS boundary at r infinity. So this is the entire space-time, right? This is like from r is 0 to the ADS boundary. And so what we see is that for a single mode, there is no V dependence, right? So as I move around this circle, this is the argument of the complex coordinate psi, and this is exactly V dependence. So for a single mode, this is circular symmetric. There's no V dependence anywhere. There's no wiggles. We don't see any time dependence in our metric. Okay, what we see that this modulus of f squared goes from some value at the boundary to it's always going to be 0 at the origin. Okay, now this last part is still true when we have a multi-mode solution. So here we've plotted for sine of psi, because why not? And so for a multi-mode solution, you have the origin is still going to be where the function vanishes, right? Where sine of 0 is 0. So that's always going to be true. The structure of the cap at the cap is going to be sort of the same. But then when we move out, we see that there's phi dependence, right? There's obviously explicit circular, there's dependence on where you are on this circle. And so here we already see something that's very interesting. We see that the modulus of f squared is very peaked in value, right? It's largest where this thing is the most blue. So it's peaked here and here. Okay. So good. That's what I'll be coming back to a little bit later. But so this gives you something this is something very interesting, because you can sort of peak or localize where your momentum is, right, in the v direction. So it's not going to be just smeared out like your single mode solution was. It's not going to be just smeared out everywhere along the compact circle. That's something that that I think is very important. And so I'll revisit that in about 5 or 10 minutes. Okay, so maybe pause here for a little bit of for any questions on the holomorphic structure. Still, I'm going to talk for like maybe 10 minutes on the reduction.
Just like to make a quick comment. There was this whole process of ad hoc procedure that Daniel mentioned in passing, which we call coiffuring, which really was taking the hair that you put on the solution and smoothing it out. And it was a procedure where you just set certain Fourier coefficients to products of other Fourier coefficients. But it's all in this holomorphic language. I just want to reinforce it's encoded by the fact that the metric only cares about the modulus squareds of holomorphic functions. That's what always turns out. And so once you write in holomorphic variables, the fact the metric depends only on modulus squareds or of things is just makes all of that stuff so much simpler.
Yep. Yeah, thanks.
If I may ask, actually, is it true in general that it will always be depending on the model square of the holomorphic function, or is it only for the example that you could treat where you have only one free function and you have a particular ansatz so that it works?
Well, for the examples that I guess we don't know the general solution, because I mean we don't know the answer to that for the general function of 3 variables, because we don't know the solution for the general function of 3 variables. But I think that's the expectation.
I think I can add just one point. There is one metric warp factor called P, which turns up as the warp factor in front of the 4-dimensional metric. I think that is always going to be the modulus squared of functions. It's what Daniel's alluding to is there are other metric functions called omega and f, which you have to solve differential equations. So it's far less obvious.
But P is just a polynomial, so that makes sense. I'm talking about f here mainly.
Yeah, we don't know.
Yeah.
This is the short answer. It works in every single example we've looked at, but the fact is, at least in P, it's obvious because it's Z1, Z2 minus Z4 squared.
Right.
Coiffuring makes that the modulus squared of a holomorphic function.
Yeah, by construction, that's what the coiffuring does for you. But yeah, the other functions is exactly where you might run into problems that we don't know.
Sorry, Daniel, a question here.
Yes.
I'm Francisco Morales. In the slide, you wrote the square plus Hermitian conjugate, not the modulus square. What do you mean precisely here?
Yeah, sorry. So you're referring probably to, where was it? No, yes. Here maybe?
Yes,
right.
This square means modulus square or a square?
Ah, yes, thank you. Very good. This is squared. This is really squared. Yeah.
This is really squared. Therefore, it's not a modulus square.
No, that's right.
But let me add, the actual function that appears in the metric is Z1 times Z2 minus Z4 squared. And so that produces the modulus squared. Right,
exactly. So the way that these guys interact is exactly going to be so that, all of this stuff goes away, all of the G squares goes away, and what's left is going to be only modulus of G squared.
I see. Exactly. Okay, thank you.
Okay. Okay, I think I'll go on then. Yeah, thanks for the questions. Very good. Okay, good. So now let's turn to sort of a slightly different tack. I think, if you're not familiar with Superstrata, then you will probably agree with me that this is a complicated system. And, there's a lot of moving parts that I probably didn't explain that well. If you are familiar with Superstrata, then you will also agree with me that this is a very complicated system and hard to solve. Okay. So we are all in agreement that this is complicated. And in particular, there's a dependence on 5 variables, as I pointed out. Even though it turns out that, asymptotically, we always have this nice structure of having an ADS3 and an S3, right? So it always goes into a nice BTZ throat and then some S3. And moreover, although this is super non-trivial, there are hints that this stays true everywhere, so not just asymptotically, for some of the superstrata. Okay, so in particular, the 101 family that I'm using so much is going to be one of these. And so for these guys, you know, if it's true that we can always sort of factor out this S3, then, you know, why not just get rid of it altogether, right? And sort of forget about all of these, all of the dependence on these three variables. And so the idea is really that, you know, a dimensional reduction is a game of making things as simple as possible by going to a lower dimension where, you know, you only need to focus on the stuff that's happening in this lower dimension. Okay. That's sort of the philosophy is, you know, the philosophy is we have 60 superstrata, but, you know, maybe we can reduce down to 3D. And I'll mention in a minute, you know, a specific problem that might be more tractable to solve in 3D. Okay, so this is where I tell you the actual fields that we have in 60, as well as those that we want to reduce down to in 3D. So the idea here is in 60, you have a metric and two scalars that I haven't really talked about, and three tensor gauge fields, which are not entirely arbitrary. You can, they satisfy a first order self-duality condition. This is why 6 dimensions is actually horrible to work with all the time. But so you have 3 tensor gauge fields in principle. Okay. We want to reduce this to a simpler problem where we have a 3D metric, a bunch of scalars, and some vectors. Okay. So in particular, this A and B indices will run from 1 to 4. So this chi A is going to be just a vector, so it's 4 scalars. This guy is a symmetric matrix, so it's symmetric 4 by 4. So there's 10 independent entries. And then this guy is going to be an anti-symmetric matrix in AB, and so this is 6 vectors. Okay, so that's the field content. Now, physically, you know, let's talk about what these guys are doing for us. Physically, these chi's, this vector of chi's, I want you to think of those as basically just being the arbitrary function that I can choose. Okay, so I can, in a superstrata, right, in a 10n superstrata, I can choose this one holomorphic function. And that corresponds to basically, you know, waving my hands a bit here, right? That's what the tildes are for. Choosing my chi's to be whatever I want them to be, right? As long as it's a holomorphic function of this variable. Okay. As for the other guys, so in particular the symmetric matrix of scalars and also the gauge fields, they're very easily just seen as the obvious generalization of a Kaluza-Klein reduction on a circle. So when you do a Kaluza-Klein reduction on a circle, you have a scalar, right? One scalar, that's sort of the what multiplies the dy squared if you're reducing over y. So you have one scalar, and then you have, which is the warp vector, and then you have this, U1 gauge field, which tells you how, you know, dy talks to the other coordinates. And the immediate generalization of this from an S1 to an S3 is simply this guy, right? So where your one scalar here becomes a matrix of scalars, and where your one gauge field becomes some Yang-Mills gauge field. Okay, don't really want to say more about this. It's just sort of just saying these are the fields that you get from a natural from sort of naturally generalizing and the Kaluza-Klein S1 reduction, which we all know and love, to something on an S3.
Daniel?
Yes.
Maybe you said this, but I have a question. So is this reduction a reduction that allows an arbitrary function of psi, or just psi, or psi, chi, and eta?
Yeah, let me answer that in this slide. So one more slide, and then I'll answer your question. Okay. So
can I also ask something?
Yes.
Are you throwing away all the Kaluza-Klein, the higher modes? Or?
Yeah, so this is a consistent reduction where we're only taking into account these. We're taking into account a very specific set of these modes, right? So this is also going to be tying into why we're only allowed to take certain superstrata down to 3 dimensions, is because, you know, the other guys are going to be higher Kaluza-Klein modes, and so yeah.
And will the solution regular after you reduce it?
The 3D solution, you mean?
Mm-hmm. Yes.
Yes. So the 3D solutions that we've looked at are just regular when we reduce them. Yeah. I mean, and this sort of had to be true in the sense that the sphere dependence that we throw out, as it were, is always just factorized. So the three-dimensional metric itself is, I guess it doesn't have to be true, but this is true in the guys that we look at. Yes.
Well, in general, it's not true. When you reduce, in general, you get more singular solutions. So.
Right. Yeah, and at the end, I'll also say something about this for sort of the next step, what we want to do with this. But
yeah, thanks.
I think if you reduce a smooth solution, you usually wind up with a smooth solution, don't you? Or do you?
No, that's not true. In general, even you can start, when you go up, you have a chance to have something which is non-singular.
Yeah,
on the contrary, if you reduce a bubbling solution to 4 dimensions, you get a multi-center solution which has singular centers. So generically, if you reduce a smooth solution, it doesn't.
You're right. Yeah.
So there was another question, I think, or Guillaume, or no?
No, I was just going.
Oh, okay. All right. Okay, so I'll just move on with what I wanted to say here. So again, I'll come back to sort of what the modes are that we're going to that we will or will not take into account in just a second. What I just want to point out here is, for people who aren't maybe familiar with how these reductions work and what they do for you, is we have this very complicated sphere dependence, right? So in particular, in a few slides, I'll also show you this. The Superstrata solutions, they mix the dependence on the ADS3 and on the S3 coordinates. There's dependence everywhere. And so it becomes very hard to solve this in general because you have all these 5 dependence on 5 coordinates everywhere. But the reduction, things that fit into this reduction are so nice, are so beautiful in that they fit all of the sphere dependence into this nice function delta. So in the metric, it's just this function delta that appears, which is just basically saying that, if you give me these 3D fields like this symmetric matrix, then all of the sphere dependence is just completely fixed by that. And I don't have to think about it anymore, right? If I would have written this out in terms of the sphere coordinates, et cetera, it would be very complicated, very horrible. But when I package it in this nice reduction formalism, then it becomes manageable.
Actually, can I just interrupt? Can you go back a second? Yeah, just to interpolate. Sorry, the thing I should have said is that when you do a reduction, you can get singularities, but those singularities are usually associated with the compactification manifold degenerating in some way. So the statement is that the reduction is smooth if the manifold doesn't degenerate, and if the manifold degenerated, this thing delta would blow up with a singularity.
Right. I mean, I think, yeah, you could have a singularity if, for example, your 3D metric blows up and then these guys blow up in exactly the way that cancels this in 60,
sure.
Right? Something like that. I think that's what it okay. So as was sort of alluded to a little bit, which superstrata can actually live in 3D. So, again, we have sort of this arbitrary function here for a general superstrata, but because we're taking into account, the sphere dependence of the superstrata has to be fixed because, we're fitting it into a specific reduction ansatz. And so the sphere dependence in these complex coordinates comes in chi and eta. So I'm using this notation here. Apologies to anyone who's colorblind, but that the red coordinates here, the red things are things that depend only on the 3D. The blue things are things that live on the sphere, and then purple is anything that mixes the two, right? So these guys mix the two, and so the dependence on these guys is going to be restricted. And so in particular, this means that, you can go to arbitrary n, so arbitrary psi dependence, but the dependence on these chi and eta guys is going to be very restricted. So that should answer the question of which superstrata go down. And now this is again to the same thing that I flashed you before, which is the 10n solution. And before I was trying to convince you that this was so beautiful and simple. Now I want to convince you that it's horrible and complicated because look at all this stuff and look at all this dependence on the sphere. Again, sphere is blue, ADS is red, and then purple is mixing. Look at all this mixing. Look at all these purple things. But when we reduce this guy down to 3 dimensions, we get this very, very, very simple solution, right? So in particular, my symmetric matrix just becomes some diagonal matrix, which depends in a very simple way on the modulus squared of my function. Again, repeating what I said before, my chi's are just related to the arbitrary function that I choose. And then I also just need to take 2 gauge fields turned on, but they're also very simple. One is just trivial, and another one is fairly simple. And even the metric, 3D metric, depends very simply on these guys. So this is just, again, this is just sort of flashing the system to try to convince you that, look, it's a lot easier in 3 dimensions once you've reduced it. So I've, in a sense, the 1, 0 for the 1, 0, n, you've seen me simplify it by introducing holomorphic coordinates, and then simplify it even further by reducing it down to 3D. Okay, so I'll pause here for questions and hopefully wink at the organizers to let me go for another 10 minutes, because hopefully that's all I'll need for this last part.
Should we can I make a comment just back on the previous slide?
Yes.
The other thing that we hadn't noticed before is you look at the 3-dimensional metric, du plus dv is time, or dt, and that's a time type vibration over a non-compact non-compact Taylor manifold. And so that's also a huge simplification. The geometry of the 3-dimensional space seems to be generically a time vibration over a holomorphic space.
Yeah, and
sorry, just one question. Are you missing the square in the metric?
Yes.
Oh, yep, I am. Yep, right.
Okay, thanks.
Thank you.
Yeah, go ahead, Daniel.
Okay.
Yes.
Yes.
Actually, you might come back to this, but this is the solution you had already in 6D. Have you started to study what would be beyond in the 3D truncation when you?
Yeah, excellent question, right? So, no. So one further direction is sort of to explore this 3D system more, in the sense that, at this point we've reduced it from 6D to 3D on the level of the equations of motion and the action, but we haven't looked at supersymmetry. So one next thing that we want to look at is supersymmetry. And in particular, we want to understand, how do these guys are obviously going to be supersymmetric in 3D as well. And it seems like this holomorphy of, let's say, this combination of scalars should pop out of the supersymmetry equations as well. And like Nick also said, the structure of the 3D metric should also pop out of the supersymmetry equations. And that's something that we really want to pursue. And another thing that we want to pursue, I will talk about in just a minute. Yeah, but we haven't done it yet, but this is definitely like the next step. Yes.
Can I ask, just for the philosophy, do you hope to get new solutions from 3D and then uplift them in 6? Absolutely, yeah. So I mean, this is definitely a time that I should segue into this. Yes, I mean, that would be definitely the idea, the hope, the strategy, right? So we've now reduced our system down to 3D. Once we know what the 3D SUSY looks like, which we don't know yet, there's one obvious thing that we want to consider, and that's to try to find more general superstrata, right? So in 3D, the hope would be that it's a little bit easier to study the supersymmetry equations. And in particular, one thing that we would like to see generalized is the 4D base that we start out with in 6D, which is always taken to be fixed and flat. If you remember these 3 coordinates get deleted in the reduction because we reduce over these S3 coordinates. And so what you're left with is a much simpler solution in SUSY. And so we know also in 6D, from the 6D supersymmetry equations, we don't need to fix this guy to be the simple flat 4D base. All we know is that it has to be almost hyperkähler, and also that it needs to satisfy some complicated nonlinear equations that we don't know how to solve in general. But then the hope would be that, reducing it down to 3D, we might be able to find new structures, new solutions that when we uplift them again to 6D, become new 4D bases for us, right? So that's sort of the idea, is that the 3D SUSY, so this is sort of the supersymmetry approach, studying the 3D SUSY will lead to new solutions in 6D, which have new 4D bases, right? So new families of superstrata. Okay, and so that's one thing. The other thing is not supersymmetric. So moving towards finding solutions that are not supersymmetric. And so how do you go about that? Well, let me say this in a few steps. So the first thing to say is, okay, remember the old single mode superstrata were smeared over this compact direction, right? In the sense that there's no dependence on V, right? Everything is just uniform in V. There's no time dependence of the metric or anything. Okay, so
this was the old single mode solution this is just the thing that I plotted before. And then remember, I plotted this sine function here before, which gives us some structure, right? Which shows, excuse me, that you have some peaks, that you can introduce some peaks of this, of where this modulus squared becomes high. And so this means that you can introduce peaks, you can introduce localization of where this momentum charge is really in the v direction. And in particular, you can go very extreme to this. So you can go even more extreme. And this is something called the wrapped Cauchy distribution, which, you know, for our intents and purposes, it's something that's very localized and depends on some parameter gamma, which you can tune. And so these are two graphs. And so this gamma here is 1, which gives you a very highly peaked thing around 0. When it's even smaller, then you get an even more peaked distribution. And so the thing that I want you to see here is that you have, you know, on the boundary, right? So on the ADS boundary, you have a very strong structure. You have a very strong peak here of your momentum charge. But as you move inwards, this structure is more or less washed out because you always need to have basically the structure disappearing at the cap, right? And so here you see, you know, there's a very strong peak, and as you move inwards, there's less and less structure and it disappears here. Same thing is true for the really high peak, even more so, right? You have a lot of structure here, and it gets quickly washed out as you move towards the center here. Nothing is stopping you in the BPS solution from just having 2 peaks, right? From having as many peaks as you want. This is as a holomorphic function. This is just simply having some kind of superposition of 2 different holomorphic functions, or, you know, sum of 2 holomorphic functions. So, so this is in particular, you know, I have a Cauchy guy over here plus a Cauchy guy over here. So I have 2 peaks. And again, in the center, the structure is washed away. And so how would we make this, or how would we use this as a stepping stone towards a non-BPS solution? Well, from the point of view of the 3D equations of motion, you know, you have 2 null directions, right? You have u and v. If you remember, this is the v direction here because my complex coordinate is basically like, you know, e to the iv. But these 2 null directions are sort of at the same footing, for at least at the point of view of the 3D equations of motion. There's no reason why one is more important than the other. So what you could imagine doing is you can imagine taking a solution and flipping v and u, okay? And so this would just give you, instead of a right-moving localized momentum wave, a left-moving localized momentum wave, right? Something like that. But then what you could imagine is you could sort of take one of these guys and keep it in v, and take the other one and flip that one to u. And that would give you something where both of these structures here, both of these peaks would be by themselves BPS, because they're just some localized BPS momentum wave. But because they're, you know, moving in the opposite direction, one left and one right moving, together, these would definitely break supersymmetry. And so the solution would hopefully be something that we can find, because again, like I said, the structure is more or less confined around where your peak of momentum is. So the idea would be that we could try to construct non-BPS superstrata using these sort of these 2 techniques together, right? So the first technique is using the holomorphy to localize your peaks, your momentum peaks, and the second technique is using, I guess I didn't really say this explicitly, but using it in 3 dimensions where we forget about the sphere. We only have 3 coordinates, and we consider just the equations of motion in these 3 dimensions, which hopefully are something that either we can solve, you know, perturbatively in R, for example, as we go 1 over R towards the center, or even numerically, you know, we just say I have boundary conditions of having a peak left moving here, peak right moving here, and then, you know, integrated it into the center and see what happens. So good. So that's sort of the end of the story. Let me just come back to Kostas's comment about the singularness. It's of course possible that, you know, when you integrate this kind of system, when you find a solution where you have these let's say anti-BPS waves, that you'll end up with a singular solution in 3D. It's possible that you'll end up in a singular solution in 3D because you need to turn on higher Kaluza-Klein modes in the full string solution, which might be non-singular. So that's something that we might see, you know, if we do this in 3D, we might have something singular, and we might be able to realize that this is because we've sort of cut off the higher Kaluza-Klein modes that exactly sort of come in to resolve the singularity. This is something that, you know, this is work to be done, right? But I hope this is something that we can do soon. Just to summarize really quick, and then I'm done. I hope I convinced you that, these two tools that I introduced to make microstate geometries simpler to deal with, which was the holomorphic structure that led to, being able to find arbitrary functions of one variable, new solutions that depend on arbitrary functions. And then the second tool of dimensional reduction, that these tools are very useful in studying superstrata and also hopefully finding and understanding new solutions. So in particular, from the supersymmetry point of view, we hope that we might be able to find new families of superstrata, in particular new 4D bases. And the holy grail, let's say, is finding new solutions that are non-BPS from colliding these, if you will, anti-BPS holomorphic waves that are localized. Okay, I'll stop there. Thanks.
Nicely done. Okay, so questions, people?
Can I ask one? So this holomorphic variables, if I remember correctly, they were also parameterizing an equator in S5.
Yeah.
So why is it S5?
A hemisphere, yes. Sorry.
Hemisphere, yes. Why is it S5 showing up in the system?
I mean, I think the short answer is we don't know. Yeah, we don't know. When you sort of stare at the supersymmetry, the BPS equations, and you rewrite them in a nice way, you can rewrite them as operators on the S5 if you really want to. And maybe this is the way forward, but I think the short answer is we don't really know exactly why this has to be true. Yeah.
And that supersymmetry require holomorphicity, or was it, let's say, some specific solutions which are holomorphic, and then maybe more general ones which are supersymmetric but not holomorphic?
I think this is sort of tied into the question that Nick answered before, where if you allow for negative powers, so breaking holomorphy, then you end up in general with, I guess, singular solutions. If you were to just solve the equations like that, you end up with singular solutions. And it seems like BPS or the SUSY conditions force you into having only positive coefficients.
I think it's going to be clearer when we do the three-dimensional BPS analysis. I suspect that holomorphy is just going to be the way it gets phrased in a very nice way.
Right.
6 dimensions, it's much less obvious.
Yes.
But I've got one comment I want to make soon, but I just want to let other people ask questions first.
Okay. There was a question. Emil raised his hand.
Yeah. So on this last point about non-BPS solutions, so what's the intuition behind using the form of the BPS solution to describe non-BPS solutions? Is the ansatz sufficiently general to characterize a non-BPS solution?
Oh, okay. So what you're saying is, will my hopeful non-BPS solution fit into the same like metric ansatz with the nice decomposition?
Yeah, with a bunch of nice harmonic functions, etc.
I mean, I don't think that's obvious at all that would be true. I mean, I think at being maybe optimistic, asymptotically, we would expect that near each of these peaks, the metric would look, of course, of this form, right? Because it has to be, because it's going to approximate the BPS solution to a good extent. But then once you go inwards, you're going to have V and U dependence. And so, I mean, I almost don't see how it's possible to keep the same form of the metric, because you're going to...
This is exactly the comment I want to make. So you should look at this as an initial value snapshot.
Yes.
Because remember, the left-hand lump, if it's BPS, is left moving, and the right-hand lump, which if it's anti-BPS, is right moving. So if you let it go in time, these two spikes are going to collide and pass through each other.
Right.
And scatter and produce all sorts of cool stuff, perhaps gravitons or whatever else. So this is
a singularity.
Or a singularity. It could. What I expect will happen is they'll keep passing through each other, and every time they pass through each other, they'll produce some radiation. And then they'll finally settle down possibly into a singularity, possibly just into some mush. But this is the thing is that, exactly as Daniel said, the BPS equations, you could easily say, I want to do anti-BPS, and all it does is it exchanges U with V in 3 dimensions. It also does it also in 6, but it's a bit more complicated to see. So BPS and anti-BPS are easily written down. They produce exact solutions, and if you keep them widely separated, they are, to a very good approximation, depending on the separation, the exact solution. And so you should think of this as a way of precisely framing an initial value snapshot. You're going to start with this as the initial data. 3-dimensional equations are much easier than 6-dimensional equations. And so the hope is we'll either be able to do this perturbatively or perhaps even numerically. But this is the first time where we can frame an initial value problem with precision, where we know exactly what the CFT states are as well.
Okay.
So can I go back to the reduction?
Sure.
If you go back, just a comment and a question. So here, the story was that you were focusing on the metric predominantly when you were, here, you have the metric ansatz and that you sort of fit everything into the massless modes.
Mm-hmm.
The tensor gauge fields, which are the matter supporting the configuration, even for 10n single mode, do depend on one of your angles on the S3.
Sure.
Right. So just to clarify, I think the previous discussions, I think you're not reducing the whole theory and truncating only to the massless modes in 3 dimensions, right?
So,
you're reducing the metric, I guess, and so, even when we did this for the 10n single mode, we had this question of, okay, how should one think about the tensor gauge fields, because they will have all the higher KK modes there are in some sense necessary for the whole thing to be smooth. So so the question part is, did you guys make any progress on understanding the whole 3D theory as a theory of massless and massive KK modes?
Okay, so is your question, so in particular, I think, I'm not sure if you can you see this PDF that I opened? Or?
No, we're still seeing a PowerPoint.
Oh, okay.
It's a sharing, so you have to share a different document. So just stop, press
up. Okay, I'll stop and then I'll just share my screen like that. Now you should be able to see everything. Okay, so these are the 3 forms, the reduction of the 3 forms. So in particular, you'll see things like, so this is for the 10n, the particular truncation. So I mean, if your question is, do we understand how the 3 forms fit in this truncation? Then, this is, for example, how it
okay, great. So can you then say how the dependence on phi 1 comes into the story?
Well, I mean, in a sense, here's the answer, right? This tells you exactly where the dependence on all of the sphere angles comes into. Is that your question, like how the?
Yeah, no, I think you're answering the question. So this was Costas' question: are you truncating the whole theory down to 3 dimensions just to the massless KK modes? And I think your answer is no.
What do you mean by massless KK mode?
Well, yeah, so you're on a sphere, so it's sort of.
It's the lowest mode. It's the thing that you always do in a consistent truncation. You take the lowest set of non-trivial modes, pretty much. So basically, as he said, sine theta e to the I phi and cos theta e to the I phi 2.
Right. So in particular, like if you think of, if you think of these things, right, like this guy tells you which modes we're taking into account, basically, right? And so we're not taking into account anything more than, like a sine squared, right?
Great. Yeah, this is what I wanted to see. Okay, good.
Okay.
So what's the 3-dimensional theory? Can you show us the action?
Sure. Well, this is the truncated version. The full version, would you like? This is
to the top.
Obviously on archive, but the full action, sorry, it's
section 2.6
because I have Zoom stuff also in the corner. Here, summary. Okay, so this is the 3D action here, 2.40. And so it's a very simple theory, but I think what you're most interested in is probably the potential. Is that what? Yeah.
Well, I just wanted to see exactly, what dynamics you're keeping. But
Right. So the potential is given down here.
Good. And the second part of my question was, you said you could do relatively low values of the integer parameters k and m. So
Yes.
can you say more precisely what the scope of the current technology is?
Which values?
Yeah, and whether you could generalize that further, for instance, to more general values.
Yes, I can say some things about that. In particular, let me say, oh, okay, no, that doesn't work. Here. So yeah, in particular, so the values that you can reduce are, so the ones that you can reduce explicitly, that we know explicitly how to do, are the 10n and the 11n, and also the combination, which is the 1mn. So this is basically just the combination of these guys. And I think we have reasons to believe that that's probably all that's going to fit into this particular truncation. So in particular, you might somehow, you might think that, for example, the 21n might fit into that, because if you sort of stare at the angular dependence, it's still sort of just, what is it, sine theta, cosine theta, something like that. But you can fairly easily see that it does not actually fit into this S3 reduction. Now, I think Nick and Robert Walker have ideas about, well, I guess they know that they can reduce it down to 5D, and then you can probably reduce that on an S2 down to 3D. I don't have anything to say about that. I don't know much about that, but
I think
that
there
might
is
be a way to go.
I think there is a consistent truncation that does 2-1n, and it is a two-sphere reduction of 5-dimensional supergravity. And the point is that sine theta, cosine theta, which makes sine 2 theta, it's cosine squared, sine squared theta, which makes cosine 2 theta. So the angles get double, but I think it's a consistent truncation. I have another remark about consistent truncations, but I want to let other people speak. We'll ask questions first.
Yeah, does that answer your question though, David?
Yes, yeah, thank you very much. Cheers.
Okay, let me add another comment. The three-dimensional consistent truncations are a very rich structure. Henning Samtleben has this stuff with Nicolai. There's a huge body of work. And it's there's even a paper with Nicolai and Samtleben where they've actually argued that perhaps it's a consistent truncation that involves a whole infinite tower of all Kaluza-Klein states of one of the tensor gauge fields. They call it, there's an SO8 infinity theory, but that infinity is made up of the entire Kaluza-Klein tower of tensor gauge fields. So it's possible you can rewrite a much larger six-dimensional theory in terms of some three-dimensional theory with a large scale degrees of freedom. But for the moment, we really want to make non-BPS things, and this is the best idea we've had for actually getting non-BPS guys. So any other questions?
Yeah, Daniel, like a heuristic question. So these new coordinates, do they in any way help in like counting the number of states in the style of Ryczkov?
Oh, yeah, that's a cool question. So stay tuned, I guess I would say.
Okay.
So I'm trying to figure this out, like in supergravity directly. So Masaki had this. So I cited this paper before. Masaki has this paper where he counts all the superstrata using CFT arguments, basically. But you can also directly do this in supergravity. So like Ryczkov did this directly in supergravity for the D1, D5 system. You should be able to do this as well for the superstrata, and in particular for the superstrata that we have explicitly. That we have the explicit solutions of, you should be able to like crank the wheel and find the right symplectic form and count them and all that. So yeah.
So do you expect? I mean, these new coordinates don't add up new solutions. So in a sense, you should match with the CFT results of Shigemori.
Yeah. Well, I mean, you should have it's a way to find all of the solutions that you need to count in a way.
Right, but that would be nice, consistent check if up until here, for that many solutions, the CFT and the gravity calculations agree.
Yeah, I mean, the all of the states that you count, of course, with this counting of superstrata, I mean, not all of these are even constructed yet, right? So this is sort of more of a counting of all. So if we know how to write down the most general superstrata in this formalism, that's two arbitrary functions of three variables, like I showed you, then the counting can be. Then this is the paper that tells you how many superstrata we have. right? And so, but these are not going to be all of the these are not going to be all of the microstates of this black hole, because this counting tells us that we are missing something, right?
Right, but in principle, you can identify in terms of CFT operators what you're missing. Is that true statement? Or?
Yeah, right. We definitely, I mean, there's certainly some understanding as to which states are missing in the CFT. Yes.
I think we should wrap it up here because we've got another talk in 5 minutes, and be good to have a 5-minute break. So thank you again, Daniel. Nice done.
Thanks.
Thank you.
Thanks. So I'll put everything on mute for the next 5 minutes, like a forced mute. So then, and then once Samir comes, I'll activate his microphone and I'll allow people to unmute themselves. Nick, can you put the conference header?
Joseph?
I'm trying to make Samir co-host.
Yep, you've done it now.
I think I've done it. Okay, so I think we can start. We can just check. Samir, can you hear us?
Yes. Can you hear me now?
Yep. Yes. Just give it a couple minutes and then we'll kick off.
Absolutely.
Okay, so I think we should start. It's a pleasure to have Samir to talk about his.
The muting.
Sorry, it's the problem.
I need to change the muting system. So I think I've just muted everybody. Samir now can unmute.
Yep, I was just thinking about introducing. So anyway, Samir, please, you can talk about the Vector hypothesis.
You need to unmute first.
I am unmuted, I think.
Okay,
Yes.
I just pressed something called unmute. Is that what you wanted me to do?
They can hear you. Perfect.
Good, then take it away.
Okay, thank you for the invitation to this wonderful conference. I'm going to be talking about some ideas I've been developing over the past several years, and they are listed in these papers down here. In particular, this last one, which is in fact titled the Vector hypothesis, where I've tried to collect all the ideas together to arrive at a picture of what I would like to say. So as we know, the quantum theory of black holes presents many paradoxes. And in my opinion, the main ones can be listed as follows. First, we of course have the information paradox, which comes from this pair creation around the horizon. Then we have the bags of gold problem, or the problem of unbounded entropy, which says that you can store an unbounded amount of data inside the black hole horizon. So that conflicts with the Bekenstein value. And then there are questions like, what happens at the cosmological horizon, for example, the de Sitter horizon, and is that really different from a black hole horizon? So actually using the small corrections theorem, each of these puzzles can be converted into a sharp contradiction with the behavior of semi-classical gravity. And more generally, we can ask the following question: is the behavior of quantum gravity the same at all different horizons, the Rindler, the black hole, the cosmological horizons? So we have all this collection of puzzles in how quantum gravity behaves, but we will argue that all these puzzles can be resolved by adopting one common hypothesis, which is the following, this thing listed here in red. The vacuum wave function of quantum gravity, it contains a certain component, which I call here the Vector component. I'll explain the term as we go along. And this component is not normally a part of our traditional picture of the vacuum. But if we take this particular component of the vacuum into account, then all the different puzzles get resolved, and all the different pieces of the jigsaw that quantum gravity has presented all fall nicely into place. So this word vector stands for virtual extended compression resistant objects, and a little preview of the idea can be just seen from this little picture I have drawn on the bottom right corner. So in the fuzzball approach, suppose this dotted line is the radius of the horizon of an object of mass m, then this brown region there is what you actually get in string theory, the fuzzball. So it's not the vacuum region for traditional classical gravity. But here you have the fuzzball, and that's the kind of fuzzball constructions we all try to make. But then outside the fuzzball, there will be excitations of virtual fuzzballs. So for example, the vacuum, even if there's no energy anywhere, there can be virtual fluctuations of electrons and positrons. I mean, they are objects of positive mass, but you can still have virtual fluctuations in the vacuum, which itself has energy 0. You can have virtual fluctuations of these positive energy objects, or in fact of positroniums or benzene rings and so on. Anything you can have a fluctuation of. It's just that we don't normally think about those fluctuations because a benzene ring, for example, is very heavy. So the fluctuation would be very rare and you wouldn't care about it. Now here the fluctuations I'm talking about are the fluctuations to black hole states of larger mass. So they are fuzzballs of larger mass than the mass m, which you actually have. So are these fluctuations possible? Well, yes, of course, because any fluctuation is possible, but is it likely? And the point is, again, any given such fluctuation will be highly suppressed if the mass m is much bigger than the Planck mass. But of course, then we have to come across the fact that the number of possible fuzzball states is very large, e to the s Bekenstein of m. And we'll argue that this largeness of degeneracy can offset the intense suppression you get because of the large mass. So in fact, these virtual fluctuations are actually an important part of the wave functional of quantum gravity. So in fact, what will happen is that if we do not assume that this tail is there and give it the property that we are going to give it today from the various things we know about black holes and fuzzballs, then in fact, we have some puzzles with causality in semi-classical gravity in situations where, for example, a black hole is about to form. And conversely, if you assume that causality holds to leading order in gently curved spacetime, something that most people would be willing to require, then actually we'll argue that you must necessarily have this Vecro component. It's not that you can get away with this by choosing to have it or not have it. You must have this component. So this light orange area here are the virtual fluctuations. And as I said before, they are important even though they are massive, because there are so many of them. And this little halo that forms around the actual fuzzball is very important. And that will actually lead to the resolving of paradoxes in the black hole case. And then it's analog also in the cosmology case. So before I go on, let me say the questions we are asking here are all qualitative questions, like what happens when something is reaching its horizon radius. So discussion also will be in terms of qualitative pictures. And the actual concrete calculations are, of course, that when you actually start to construct fuzzballs, which many of you I know are doing, but we are here just trying to put it all together into an overall picture of what must happen in different situations where horizons are about to form. So I must confess, I found this a little difficult talk to make because everything is in terms of pictures. And so if something is not very clear, please bear with me. So one might think that all this putting together everything in a picture is after all just pictures. I mean, it won't tell us anything except for the fact that the puzzles are resolved. But that's not so. Once you have this Vecro component which you need to resolve the puzzles, it also appears to be having an impact in how we think about gravity in many situations of interest. This is just something I'm working on. So this is more like something I'll think about in the next few months. But it seems from a first analysis that the Vecro component may affect our picture of bubble nucleation and inflation, etc. For example, if you have a bubble in normal gravity, one difficulty with the old inflation was that the bubble expands at the speed of light, and a thin wall bubble has all its energy in the bubble wall, and there's no energy deposited inside, and that creates a problem with cosmology. So in fact, the old inflation model was discarded. But it appears that with the Vecro picture, bubbles actually cannot inflate at a speed approaching the speed of light. In fact, the speed must always be less than half the speed of light. And that means the energy can't all be in the bubble wall and must be distributed throughout the volume of the bubble. So there you have a severe change in the behavior of what you thought you would get from classical gravity. And that shouldn't be completely surprising. After all, we have to change the entire interior of the black hole to resolve the information puzzle. So of course, it will change physics in other places as well. Okay, so before I go on, I just want to check, can people see this mouse as I move it across on the screen?
Yes, yes.
Yes, no problem.
Thank you.
And are you going to explain that thing about the bubble?
Yes, towards the end, my last two slides will be on that. So if I do have time, I will explain that. Okay, let me just begin with a very brief review of fuzzballs. Many people have worked on it. Many of you out there in the audience are much bigger experts than I am. I just listed a few of the people here who have worked on it, but of course, many others have. And all the qualitative pictures I'm going to talk about is really built on the work which all these other people have done. So okay, just a brief review of the fuzzball idea for those who have not been actually working with fuzzballs. Consider the bound states of, let's say, D1, D5, and P charges, like the one that Strominger-Waffer took. So at weak coupling, the bound state would have some size, maybe like Planck length or string length or something. And one might have thought that as you go to strong coupling, the bound state remains small, like Planck size, but then around it, the normal gravity solution develops, which has empty space everywhere, and then maybe a horizon, and you get the normal black hole. But actually, when you try to estimate the size of a brane bound state, that's not what you get. If you have N1, N5, and Np as the numbers of these branes, and G is the string coupling, and V and L are parameters of the compactification that you have, and you find the size of this D1, D5, P bound state, then you find all those 7 parameters involved in there fit in a particular form to give the diameter of this bound state, to estimate the diameter. But that's exactly the same form which you get for the radius of the horizon of a black hole with those charges and at that coupling. So this actually suggests that you don't actually manage to form traditional black holes in string theory. Whenever you try to make a bound state of branes, it always sort of expands to become more like a planet or a string star. And then, of course, that will take care of your information puzzle. So as I was saying, many examples of string solutions have been constructed. And in each case, one has found the solution has no traditional horizon. And there's a large program initiated by Bina and Warner, which has made a large class of these solutions. So then it all just runs into the fuzzball conjecture, which would just say that no macrostate in string theory will have a traditional horizon, which is one which has a normal vacuum in its vicinity. And because if you had normal vacuum, then that's defined as something where you get the normal entangled pair creation, which you can schematically model like this, up to any small corrections, because you can get small corrections from anywhere in quantum gravity. So traditional horizon is something where you would get the normal vacuum, like in this room around the horizon, that will obviously then by definition lead to this pair creation, and we allow small corrections. if that's what you call the traditional picture of the black hole, the Fuzz-Ball conjecture says that no macro state in string theory can ever actually be like that. Instead, if you get the stuff which goes all the way to the surface, it's like a planet, and there's no region like this vacuum around the horizon.
I have a question, Samir. Can I interrupt?
Yes,
here?
please. Yes.
Sorry, yeah, this is Subrat. The question is, when you say traditional vacuum, are you referring to the complete fine-grained wave function, or is this a statement that low-order functions, correlators of the metric, will behave the way they do in a vacuum?
No, I would actually like to talk about the wave function. So actually, I don't want to talk in terms of the correlators, because correlators sometimes can give you too little information, as you also have said in many papers. So I would imagine doing the following, like if I want to ask if this room is in the vacuum state, I can still make sense of that question, even though the room is not the whole universe. But it's if this room is in the vacuum state, then if I try to find the wave function in some ball of radius 1 meter, I know when it corresponds to the vacuum and how that vacuum would behave. So if I try to make a ball-sized region in a 3 kilometer radius black hole of, let's say, radius 1 meter, I'm asking whether that is going to be up to order epsilon corrections, the same state as the vacuum state in this room. And by that, what I mean even more precisely is that does it behave like the semi-classical vacuum, that if I stretch the slice, it'll actually create the entangled pairs in this fashion. So yes, I've put all that in terms of the wave function, and that's what I really meant.
Yeah, just one question. Of course, if I change some very high energy degree of freedom, I could create a state that was orthogonal to the vacuum.
Yes.
But no low energy observation would determine whether the state was orthogonal to the vacuum or still the vacuum, because what I've modified is some very high energy degree of freedom. So you would like to rule that out as well?
I would. Yes. Yeah. Thank you for that question. Yes, I'm ruling that out as well, because in fact, we can have the discussion later, maybe perhaps in the discussion session. But yeah, that's very crucial. If you add some high energy degree of freedom, let's say in this room, that is something which I can detect. It's a change. Maybe a low energy observation may miss it, but I think many low energy observation may also catch it. Depends what you're trying to observe. But yes, absolutely. I'm saying that a vacuum means the vacuum. I'm not looking at any smeared 2-point function or something. I'm actually talking about the state. So thanks for that question. Okay, so with that, we can still ask. So in some sense, you can say we've solved our puzzle. If the states look like that, and we have enough data to say that maybe they all look like that, then we are done. But actually, we'd really like to understand what happened here, because if you take something like Buchdahl's theorem, what does that tell us? If you take a sphere of a perfect fluid, and you make that sphere have a radius which is less than 2¼ m, then the sphere can't support itself against this gravitational pull. It has to collapse inwards, and make the traditional black hole. And the way you prove that is, of course, if you put the pressure to be 0 at the boundary of this ball, and then you integrate the pressure balance equation radially, you find that P diverges somewhere before you reach R equal to 0. And then you say, okay, if P became infinity, the solution is bad in some way. So let's throw away the solution. And so you say the object just has to collapse. Now, of course, you might say the string solutions we have are not perfect fluids and so on. And of course, that is true. But the spirit of Buchdahl's theorem is still there. Once something comes very close to the horizon, there's an enormous pressure trying to pull it in. And the guy doesn't want to stay there, just wants to crush. And what exactly is string theory doing that's actually not happening? So I just want to make a toy model here to do that for people who don't actually work with fuzzballs. And the reason I want to do that also is that I'll take this toy model and say that in your mind, you can hold this as a picture of the fuzzball and therefore also of the virtual fuzzballs. We're going to talk in quantitative terms about these fluctuations, but it's good to have a concrete picture in our mind so we know what we are talking about. Okay, so just a toy model. And so consider Euclidean Schwarzschild solution plus time. So what I mean is take 3 + 1 Euclidean Schwarzschild solution. That's the one given by tau, r, theta, and phi. And tau is the imaginary version of the normal time of the Schwarzschild solution, and it's been made periodic in this fashion. So these 4 variables give a Euclidean solution where the tau direction, it has some radius at infinity, but then the radius shrinks and vanishes smoothly at r equals r0. And the region at r less than r0 is just not there in space-time. It's like a hole. If you're in this room, cut a hole of radius r0, throw it away, and then you might say, oh, I have a hole in there. But no, as the compact dimension comes closer to as you approach that radius of that hole, the compact dimension smoothly closes off like a cigar. And the whole thing is actually a completely smooth geometry, which is a solution of 4 + 1 dimensional Einstein gravity, vacuum solution. Okay, so we know the solution is there. Now let's do a dimensional reduction on this tau circle, and that will give us a scalar field. Let's call the scalar field phi, which we get by dimensional reduction of this tau circle. And then you get 3 + 1 gravity. And the stress test for the scalar field is standard one for a many couples scalar field, so you can work it out. And so from a 3 + 1 dimensional perspective, you could ask, here I have a shell of scalar field. Why isn't it collapsing inwards? You can work out a stress tensor, and you find, in fact, the components of the stress tensor all diverge as you start approaching this point R equals R naught. So in fact, the pressures are even diverging. So you can see the pressures over here, and they are actually diverging. And so if you're a person like Bugdal, you would say, hey, this is a bad solution, and I don't want it. But of course, we know that's not the case. It's a completely smooth solution in 4+1 dimensions. It just looks bad from a 3+1 dimensional point of view. Okay, so we can use this as a schematic picture of the first of all, if you want to actually see the constructions, you've got to see what all these other people have been doing in their wonderful papers. But just for a rough analysis, you can just take as a picture where, in various regions of space-time, first of all, you just cut out little holes like this hole in here. Just imagine I can cut out not just one hole, but multiple holes. And at each of these holes, the compact dimensions shrink appropriately. And then the whole structure, I'll draw it a little more precisely later on, are just holds together into this big fuzz ball. So we'll just take it as a schematic picture, but of course, this is just something with a surface like a normal piece of coal on a planet, and so there's no information puzzle as such here. Okay, so with this picture at the back of our mind, let's get down to the issue that we are trying to address. Okay, so here's the information paradox. You take a big ball of gas or dust like a star, it collapses under its own gravity. Classically, all the matter goes to the center. You have the vacuum here that produces the entangled pairs, which we can schematically write as 0, 0, plus 1, 1. And then the entanglement of everything far outside with everything inside keeps going monotonically. And then you have a problem at the endpoint of evaporation. A normal body, of course, would have a curve of entanglement, which after the halfway point turns down. And in the end, the entanglement sort of goes to 0. Okay, now in the first world paradigm, of course, we have a normal object which is radiating. It's not entangled pairs being produced from the vacuum. So there's no puzzle. And you might say at one level, we are done. First world entanglement just comes down. But let's press the question further. We can still ask about the dynamics. So suppose you take a collapsing shell, it's just coming in. How does the shell actually become the fuzzball? Well, in principle, you might say we know the answer to this question also, because the fuzzballs are like the energy eigenstates of the full string theory problem. So let's call them Fi. And so if you know all the eigenstates in principle, suppose you've been able to work it out at some future date, then the wave function of the shell will be some linear combination of these eigenstates, fuzzball states. And then if you want to know what happens to the shell at a later time, you simply evolve each state of energy E, fuzzball EI with energy EI, and you know the state. So in principle, well, once you know the eigenstates, the dynamics is already there for you. But let's really press the question at a physical level. What changes in the semi-classical picture of gravitational collapse? Because if you take a shell which is collapsing, we all know that as the shell passes its horizon radius, all the curvatures and densities can remain low, and so nothing happens over there. And then if nothing happens over there, in the semi-classical picture at least, then as the shell goes to the singularity, well, there something new could happen because it reached a high curvature region, but the light cones in the region between the shell and the horizon radius actually turn inwards. So in fact, if you assume that you have no significant propagation outside the light cone, a small effects you can always have of quantum gravity, so that we can't stop. But if there's no significant effects that go outside the light cone, then this whatever happens in the singularity can't actually change the existence of the horizon. So the pairs would be created, and you have the usual problem. So we will assume this kind of causality. The signals don't propagate outside the light cone, and they are non-local effects and so on at large space-like separations. But given that assumption, it looks like a semi-classical argument looks sort of airtight. And what we want to pinpoint is what goes wrong with that argument. So that, of course, has always been the crucial point of the black hole puzzle, like why does the semi-classical thing break down? And we want to see if we can now understand that a little better with all that we have learned about fuzzballs. So again, before I go on, I just want to emphasize I'll be using the fuzzball paradigm for how the puzzle is resolved for everything. We just radiate like a normal planet, and you don't have the normal pair creation here, just like Surat is asking. That's really what I'm saying about the fuzzball. So if there have been many other interesting ideas about the black hole puzzle in recent times, some by Pavlo Masaraju and a lot of work by Malvicino and his collaborators. I just roughly categorize them in the wormhole category of ideas. I just list them here, but I'm listing them here to say that we are not going to actually be using those ideas. So, but just to mention, one might think that the B and C quanta, because they're entangled, one could argue they're joined by some kind of a thin wormhole. And because of that, the bits which are very far away, like the radiation goes out to distances of order n cubed, they may not be independent of bits which are inside the horizon radius. And then you could map some part inside the horizon by an island region where the bits are really part of something outside and not part of what you would call the black hole. So there's an interesting category of ideas there, but I will not be using these because, as I've said, I just assume that there are no novel non-local effects that we have to introduce when black holes come. but this black hole just burns like a piece of paper. And so at that level, there is no normal physics that I have. So with that restriction placed upon me, I want to know what actually goes wrong with this semi-classical picture. So let's then get to what is the vector idea. Okay, so the idea just goes in the following steps. So in step A, we just have said this before, the macros of black holes are like fuzzballs with no horizon, and they're extended objects. So this term we had, the vectors, stood for virtual extended objects. So the V just stands for virtual, but the fact that the fluctuations we're looking at are extended. They're like, benzene rings or something, except they can have an arbitrary radius. So the fuzzballs have a radius which is a little bigger than the horizon radius, and so these are objects of that kind. So there's the actual states, which are the on-shell states. And as we had argued right in the first slide, if some states exist as on-shell states, then the vacuum wave function must show these states also. There must be some way of seeing that effect of those states in the vacuum wave function as virtual fluctuations. So this is just schematically over here. Around every point in our space, there can be fuzzball fluctuations of arbitrary radius. I just drawn those fluctuations with these schematic balls over there. Okay, but as we said, the fuzzball fluctuation can exist for any mass m, but of course you expect a big suppression for any particular fuzzball configuration for mass m much bigger than the Planck mass. You can even try to make a crude estimate of the how damped that should be. So if you write the probability of fluctuation to be e to the minus some action, the action is like some energy into time. You put the energy to be the mass of a black hole with that radius, and for the time you can also put the light crossing time to be like that radius. You find the S is a pretty, when R is much bigger than LP, for fuzzball fluctuations bigger than the Planck length, they should be highly suppressed. And because e to the minus S, you can see, is a very small number. But then even though the probability to fluctuate any individual fuzzball configuration is very small, the number of possible configurations is very large. If you're looking at on-shell processes, you would just count the number of fuzzball states of mass m, e to the S Bekenstein, and you find that S Beck actually goes like this. So the number n, the largeness of this can offset the smallness of p. They sort of both behave the same way. And so one has to worry about these virtual fluctuations. Now, of course, right now, we are not dealing with on-shell processes. We are actually trying to deal with just the vacuum and asking about wave functions in the vacuum, which let's say has zero energy from in Cauchy space. In that, we are asking for the virtual fluctuations of fuzzballs. So here, I don't actually know how to do a more precise estimate of how things are canceling, but based on what happens for the on-shell processes, let me just assume here as part of our hypothesis that the largeness of the phase space of these possible fluctuations sort of offsets the suppression of any particular fuzzball configuration. And so these virtual extended fluctuations are going to be an important part of my vacuum wave function. So the vector component also had other letters in it, the C and the R, and they stand for the words compression resistant. I'll come to that a little bit further down the talk. The O just stands for objects. So what we'll actually learn from fuzzballs and from other general properties of black holes is that these virtual fluctuations, these fuzzball fluctuations, if you try to squeeze them or stretch them, they don't want to do that. They're like local minima, like a positronium. So certain bound state, you squeeze it or stretch it, the energy sort of increases. And that's actually going to be important. We'll set the energy scale, which comes there from our ideas about black hole physics, and that will be important to their actual behavior. So anyway, that's what the vector is. It's these virtual, just these virtual fuzzballs, and they have these properties of compression resistance, but otherwise, this is all that we're talking about. Fuzzball fluctuations in the vacuum, but their suppression because of large energy being offset by the large degeneracy. Okay, so given that qualitative picture, let's go and ask the crucial question: what can these vector fluctuations do for us? Okay, so let's make a graphical picture of what these virtual fluctuations are. I mean, the word virtual fluctuation is very easy to say, but unless you have a little better picture of what we're talking about, it's sort of rather empty. So first, let's just go and talk about just an ordinary scalar field, no gravity, nothing, just a scalar field. And let's ask, what do we mean by the virtual fluctuations of the field? So if you're in the vacuum, the classical configuration will be, if you break up the field into its Fourier modes phi k, the potential for every Fourier mode is like a harmonic oscillator potential, and classically will just be at the bottom. Now, of course, quantum mechanically, you'll actually have the ground state harmonic oscillator wave function, and the wave function has a tail which goes into all possible values of phi k, and the part of the tail which is under the barrier, potential barrier, has the conjugate momentum pi k imaginary. So pi k squared less than 0. That's what we call the virtual part of the fluctuation. But of course, the wave function goes there. So those are the virtual fluctuations. If you wanted to ask, yes, there are virtual functions of scalar quanta in this room. Where do we see it in the actual wave functional? You say, okay, I can go and write you the exact wave functional, at least in this case, exactly. And the part where the momentum squared is negative, let's call that the virtual fluctuation. And that's all it really is. Otherwise, saying I have a particle here jumping around and so on, that's just words. But this is what we really mean by a virtual fluctuation. But now let's think that the scalar field we are talking about, it actually arises at the size of a compact circle in our theory by dimensional reduction. So the size of the circle gives this phi. So then in that picture, this small fluctuation of the scalar field we just talked about, they correspond to little fluctuation in the size of this circle, right? So the size wiggles around a little bit. The metric of that can wiggle around, size becomes bigger, smaller, and those are these virtual fluctuations. So of course, we are thinking about those when we say a scalar field has fluctuations. But if you can have these fluctuations which reduce the size of this circle, you can also have these fluctuations, the circle pinches off and just leaves a hole inside. And now you can see that's looking more like this Euclid short shell thing we had taken. If you have some wave function which is peaked over here, there can be some amount of support over here. But if you go further down the tail, there should also be support on things like this. And if there are many, many configurations like this, there's actually going to be a large total amount of support, large total fraction of the norm will be supported on such configurations. Now you can maybe see a little more concretely what we really mean when we say a virtual fluctuation. It's just the tail of the wave function which is supported on these kinds of configurations, which you can see are now like the bubbles. I just drawn a one-dimensional picture. It's like the bubble we cut out in the Euclidean short geometry. And so if there are many configurations like that, then some part of the wave function leaks in there, and that's the vector part of the vacuum wave function. Okay. So we're trying to draw schematic pictures of this potential as we go along. So the picture will look roughly like this. So on this x-axis here, I just schematically drawn all possible configurations of my gravity theory, which is string theory here. So all possible string configurations over here. A semi-classical gravity configuration, let's say the vacuum would be, let's say right here in the middle, and then small fluctuations on the vacuum, let's say they are over here. So let me just also draw them here. They do cost some energy, but not much energy. So I haven't tried to make this thing curve upward, which it should. But then when you come to these vector configurations of large mass, we already said they exist, but they're rather heavy. So this potential is rather tall over here. And it's just that it's a potential in many, many dimensions because so many different configurations. And when you have potential in many dimensions, the total norm, which is under the barrier, can still be very big. So in any given direction, of course, the fall off gives you a very small amplitude. So this is the kind of wave function which I'll plot here. And you can see now, again, all I've been saying in words before, there's a tail which is supported on these vector configurations. And that's the tail which I'll be talking about. So we'll draw these potentials here. These are gravity configurations. These are semi-classical configurations. And then here are the vector configurations. And there is some tail in this vector part of the potential. Okay, so with this, let's see what will happen. Let's go back to the shell of mass m that we were talking about. If I'm doing semi-classical physics, I just have the shell and that's it. There's nothing much more to think about except small fluctuations of the normal scalar fields everywhere. Now, the wave function of the gravity state, as we have said, it has a spread over the vector configurations. Previously, we were talking about the vacuum wave functional, but now we are talking also about actually a shell of mass m. So let's talk about that now. So if you have vector fluctuations of small radius, they don't really get affected by this shell, okay? Because the shell is over here, it doesn't really overlap with this part of the wave functional. So whatever fluctuations we had there in the vacuum, we still have those. So let's not worry about them. But let's look at these large vector fluctuations, which have a radius which is equal to or larger than the radius of the shell. And then at least in the part outside the shell, the gravity of the shell will affect the vector. It will try to compress it a bit, modify the wave function. So though that part of the vacuum wave function will actually be affected. So when I draw these light orange bubbles, I'm really trying to ask about the vector configurations in the wave function, which is not describing the shell, but all the rest of the vacuum fluctuations. And so the vector distribution here will be altered. So let's try to make a schematic picture of how it will be altered. Suppose the shell is actually far outside its horizon radius. So the radius is much bigger than 2m. So here in the dotted line, I have drawn the horizon radius, and then this is the shell. You can see it's far outside the horizon radius. Okay, so then the relevant vector fluctuations have radius rv, the radius of the vector, also then bigger than r. And because the energy of a vector of radius r is like, you have the mass of a black hole of radius r, the energy will be much bigger than the mass m of the shell. So these are very high energy vectors. You probably won't have much leakage into them, but as a matter of principle, there will be some leakage of the wave function into them. So again, let's draw it on our kind of potential graph that we were talking about. Again, the semi-classical state of mass m, I'll put in the middle here. Previously, that was the vacuum point, but now we're looking at states of mass m. There's the shell of mass m, the classical state. There are small vacuum fluctuations of this, not just the vibration of scalar phase around them, but there are also all these vector configurations and to which this thing shell wave function can overlap. But because this energy gap is large, because the vectors of that radius are very big, the shell has some mass, but has a very big radius. So it's only overlapping with vectors which are very big, and those are really heavy. And the shell doesn't have enough mass to really make them on shell. So that's a huge energy gap. And so the tail of the wave function is very small. So there's a small spread under the barrier. So we'll just draw that by saying, okay, here's the shell. I don't draw the inside of the vector because that part is not affected. Here is the horizon radius of the shell. But then there's just this very light amount of shading I've done here to say there's a small leakage into those virtual fuzzballs, but nothing significant. Okay, so that's helping.
Samir, I have a question.
Yes, please.
The question is, so one could, let's say actually maybe I should have asked a little earlier. So let's say one took the action of semi-classical gravity. In principle, one could try and solve the Wheeler-DeWitt equation to try and obtain the ground state wave function. Would the claim be that when one solves this in some sense, that one automatically gets the spread on these Vecro components? I mean,
Yes,
or does one need to identify the hypothesis?
Very good question. Yes. So what I would say is, of course, the Wheeler-DeWitt normally one does for just canonically quantized 3+1 gravity or something. And that doesn't have the degrees of freedom which actually gives you the fuzzballs, right? So that's the crucial thing. If you take a theory which actually has all the stuff, so you take string theory and then you do the analog of exactly what you're saying, the Wheeler-DeWitt wave function, and just solve it for your particular state, I'm actually arguing, yes, exactly as you say, there will be this tail. And if you compute the norm of the wave function in that tail, it will be significant, it will be important. Normally the tail just goes along. I mean, if you have a wave function, you deform the classical part, it deforms appropriately the semi-classical part, and the tail also deforms appropriately. So nothing happens, the tail is there, but we don't really notice it. But what I want to argue again on the next slide is that in certain cases, the tail becomes very important. But yes, to answer your question at the moment, if you solve the analog of the Wheeler-DeWitt equation for a theory which actually has all the degrees of freedom which you require to get the fuzzballs, this would be part of the wave function. So otherwise, there's nothing novel about the wave function. You're not postulating a new kind of wave function or something. It's the wave function of that complete theory. But it's important for the theory to be complete. You just take, for example, take 3+1 canonically quantized gravity. It's not complete in the sense that the Beckstein value which you get for the entropy is still like A/4G. But you start going and looking for where are the states that account for that entropy, you don't seem to find them. You have just the no-head theorem. But if the 3+1 theory comes from, let's say, 6 extra compact dimensions, then the way those different compact dimensions pinch and twirl and do all these fuzzball constructions that people find, but that's where the entropy really is. And then you get all the e to the s Beckstein states, hopefully. So yes, if you take all those degrees of freedom and then write the Wheeler-DeWitt wave function, that wave function is also, there's nothing other magical thing going on.
Thank you. Just one more clarification, please. When one looks at the shells of a given mass, is the wave function on the Vecro component part the same as it is for the vacuum, or does that depend on the mass of the shell that one is considering?
Oh, it depends on the mass of the shell and also the radius of the shell which I have taken. Absolutely. So that's in fact the point which I'm going to make. So again, this first picture here is what we just had on the previous slide. So the energy gap is big, the shell is far outside horizon radius, the leakage into the vector part is small, so one could almost not think about it. But then in the second slide, I've put the shell closer to its horizon radius. Now it can actually overlap with vectors whose radius is, not, I mean, the vector has a mass which is comparable to its radius, like r=gm, that much of energy. But now the shell almost has that much energy. So it can overlap with vectors which are not too much more energetic than the energy which you have, the energy m. So this barrier to the vectors is a little less than this. You can see I've drawn this barrier a little lower. And so the wave function actually spreads more. And so you have a larger spread over the vector part of the wave function. You can think of like a kind of vacuum polarization. You're getting more vacuum polarization now as the shell is approaching its horizon. And if you're a semi-classical person, you'll say, okay, this tail is there, whatever the effect the tail has, the net energy you get for the wave function, including all the tail and all those effects, well, that is the net energy of the shell. So that is all included. When you say the classical energy of the shell is m, well, that's included, just like all the harmonic constant wave function we have for all the quantum fields. We know it all has a leakage into its under the barrier and so on. But all that together, finally, in the end, gives us the energy of our configuration. So yes, this is all included. But the point of drawing all these wave functions is that if you see where this actual spread is coming from, as the shell starts approaching its horizon, you see this energy gap is actually going to zero. And semi-classically, you would think, okay, I can have the shell much outside the horizon, close to horizon, but maybe I can also then just take it inside because the semi-classical formulae work exactly as well as before. So you can get an even low energy by putting it inside the horizon, and maybe in a negative energy if you put it inside the black hole horizon. But then as this thing goes inside the horizon, suddenly this energy gap actually becomes very small as it approaches the horizon and gets to the horizon, and there's no bound state there at all, and the wave function just spreads all over these fuzzball states. And then when the wave function is oscillatory over here, not the decayed part pi square less than 0, but now pi square is positive, just become oscillatory, then you actually have on-shell fuzzballs, and there now you just get on-shell fuzzballs. So if a person was not actually aware of the fact that as he's wasn't consciously aware of the fact that as his shell is becoming closer to the horizon radius, there's more and more this leakage of the wave function into these virtual fuzzballs occurring, then he would be surprised. Well, when I cross the horizon, should anything new happen? It all looks very certain. Now it's suddenly asking me for new physics. If I keep the old physics, the semi-classical horizon, I have all these paradoxes. But it actually wasn't that sudden. Once you take all these virtual fluctuations into account, really the polarization was actually increasing and increasing. And then at some point, these virtual fuzzballs just actually become on-shell. So this is a toy model which I just keep at the back of my mind. It's good for some parts of understanding this to do with the Schwinger effect. So suppose I give you two plates, charged plates, plus and minus, and I keep them at a distance d apart, but then d, suppose it is less than this critical value, 2mc square over EE, then actually you don't make any on-shell particle pairs. The energy required 2mc squared to create an electron-positron pair, you can't actually get that by separating the particles this far in the electric potential. So the vacuum still gets very polarized, and what I'll do is, but there are no on-shell particles created. So I'll assume there is a large number and much bigger than one flavors of these charged particles. So just to mimic the analog of there being many, many kinds of fuzzball configurations. So then the vacuum polarization actually, as d starts approaching this critical value, is actually quite high. The space is very highly polarized. But then when d crosses that critical value, you suddenly get a cascade where all these particles become real on-shell particles. Now, if you're a person who didn't realize that all this vacuum was getting polarized as d was approaching this critical value, you might certainly be surprised, hey, beyond this value, you say there's a huge discharge of particles, where they all suddenly come from. But actually the physics was much more continuous than that, because as you started getting close to this critical separation, the virtual fluctuations became more and more. In this case, you can write the whole vacuum wave function and see what virtual fluctuations mean. It simply means that the harmonic Auster potential for each mode of the fermion field is actually getting flatter and flatter. Just like I was showing you that those potentials are getting shallower and shallower, here you can write everything explicitly. You find if you write the potential for the electron and electromagnetic field, the quadratic potential actually gets shallower and shallower. And once you reach here, it actually basically flattens completely. Then you get the discharge. It actually turns upside down. So basically, this is just mimicking the fact that as you get closer to the critical value, you are actually increasing the virtual fluctuations. And so that is what was part of our picture here. So we can, this was just very, just a rough starting picture for us. It just tells us that the virtual fluctuations of these fuzzball type configurations are important once something starts approaching the horizon radius. And then as you reach the horizon, then there can be certainly new physics, which you might not have expected if you had always thrown away the virtual fluctuations and just taken the effective energy or the net energy you get and said, this is all I have. I don't want to look at the rest of the wave function. I'm good with everything. Forget the virtual fluctuations. Then I would have been surprised as to what happens when I actually cross the horizon. Okay, so that's the rough idea.
Question to clarify. What is the argument that these virtual fluctuations become on-shell exactly when you cross the horizon radius? I mean, I see the general picture, but why? Like, is there an independent argument that this transition happens exactly at this exactly the horizon radius?
Okay, so good question. Let me answer two things for it. First, as I was saying on a slide a little before, if you actually see the size of these vectors, there was an estimate we gave in this paper to argue that generic fuzzballs of mass m should have a size which is not too much larger than 2gm. It just order a few L Plancks larger. So it's a rough argument, but suppose we accept that for the moment. Then if you have a shell of mass m, its overlap with the vectors of mass m will happen of order 1 only when you get within a few Planck lengths of the horizon radius. So that's one part. Of course, I don't know that for generic fuzzballs. We don't know generic fuzzballs for generic Schwarzschild black hole states. But the other part of the argument you will see when we come to the information paradox, you will see something important happens when you make a horizon. So when you make a horizon, light cones turn inwards, and we'll see that that actually creates an effect which will be very important in the context of this thing I was going to talk about, the compression resistance. And so the actual cascade towards these on-shell fuzzballs is forced the moment the light cones turn over. So there is something special when light cones turn over, and then maybe that will be part of the answer to your question.
If there's any help to answer, when you look at extremal configurations and supersymmetric ones, they're actually in the paper with Bert and Andrea and Daniel Mayerson, we actually found that the tunneling happens a tiny bit before hitting the horizon. So for extremal ones, there's a tiny enhancement. So actually you tunnel when you reach the horizon size, that's when the tunneling becomes over the 1, and then you'll definitely tunnel. But you can actually compute the tunneling rate, and you compute how many fuzzballs are there, and you find that actually the tunneling rate is a bit higher than e to the minus s. So you tunnel
I think that's this kind of paper you're talking about, right? Maybe this paper you.
Yes, it's
that's very interesting to me.
A tiny bit before, but again, tiny bit.
Yes,
non-trivial.
So thanks. No, that's very interesting to me, and I should go and look at that in more detail. So roughly speaking, what's the difference in the extremal and the short-shelled hole is that there's no surface gravity on the extremal hole. So what we'll see is if there's some surface gravity, let's say for the short-shelled hole, as you get closer to the horizon in the local orthonormal frame, the pull is actually very high. Like, it actually goes to infinity when you get right to the horizon. And that's the thing which is a little different for the extremal hole because there's no surface gravity there. And so I think in that sense, the fluctuations may be a little easier. They may spread out a little more when you have an extremal hole because they're not getting sucked in as much. Yes. But actually what you said is very interesting to me. And I do want to go and see exactly, how much outside the horizon that happened. Okay, so where was I? Okay, so as we said, we need a little bit more information. So far, the arguments have been very general, just using the entropy of things and just motivated by what we know about fuzzballs. But there's one more property we need to draw from what we know about black holes and fuzzballs, and that's the compression resistance of these structures. So what does that actually mean? If you take a fuzzball kind of object, I just draw it schematically like this, but now let's take a little more detailed look at this. If you take the Euclid short-shell structure, okay, once you fix the size of this circle at infinity, the size of the, where you get this bubble and so on is all fixed. And suppose someone tries to squeeze the bubble to make it smaller or bigger, it doesn't want to do it. It costs energy. It's already a local minimum of the energy. So if you stretch or compress it, it costs you energy. And so you can make more complicated structures by just joining these guys together. But once you get a particular kind of this fuzzball configuration, it's a local minimum of the energy. So if you squeeze or stretch it, it costs you energy. So that's in a sense in which they are compression resistant. That's a little different from other extended objects like just a string loop. The string loop actually wants to compress. It's not going to fight any compression, but actually the fuzzballs are not like that. If you try to compress them, the energy will go up. Of course, nothing is incompressible in a theory which has a finite speed of light, but the fact that it will cost you energy to compress it, that's what we are talking about. If you're looking at on-shell fuzzball states, you can actually even estimate what the compression resistance is for a generic fuzzball. And that goes back to the generic idea that if I give you a radius, let's say 2gm, and an energy budget, let's say E equals m, okay, just like a black hole, then people would like to think that you can't hold more than e to the s bec of m states in that region. Like the black hole somehow gives the max amount of data you can fit in there. Now, suppose this generic fuzzball state was easily compressible. There wasn't much compression resistance. Then you apply a small force and you squeeze this generic state to, let's say, half its radius. Since you haven't applied a big force, you haven't done much work. So the energy hasn't gone up. The energy budget is still E, basically like m, but the radius has become half of what you had. So you have all those states now in a smaller radius. Okay? And if you believe that shouldn't happen, then you know that there must be some compression resistance. And in fact, you can even figure out how much it should be. The equation of state actually becomes P equals rho, the stiff equation of state, and you can actually get everything just based on the entropy idea. So we actually know this generic fuzzball state, it's good if it is compression resistant because it fits with the whole entropy of these states and so on. Of course, our difficulty right now is we're looking at virtual fluctuations. So whatever we learned from the on-shell fuzzball states is only schematic. So in fact, I'll just take it as part of our postulate. The virtual states also have that kind of compression resistance. And if people like, we can talk offline about it, and I'll try to argue that the virtual state should share these properties with the same kind of energy scales as the actual on-shell fuzzballs do. Okay, but I'll accept that as a postulate. Let me at the moment just try to make a rough model for the purposes of carrying on for what the compression resistance is. So it's just a schematic model. So just imagine a 2D manifold, and that's our space-time for now, our space. Let's look at the space part of space-time. And in that 2D space, consider a vector whose radius is RV. It's just like a disk right now. It's just a disk made out of these kind of bubbles we were talking about. And then now suppose somebody comes and bends this space. So you curve it up to some curvature radius RC, radius of curvature RC. So now you can see the vector also bends in that space. And now the outer radius of the vector, let's call it RV prime, you can see it's now become smaller than RV. And there's the trigonometry you can do that. You can see, so that when you bend space, the vector compresses. And I'll take RC to be quite large. So it's a gentle compression. So RV prime is only a small amount delta less than RV. 1 minus delta is the ratio. And you can work out delta what looks like this. So, okay, as we said, these vectors we expect them to be local minimas of the energy. So the energy of compressing the vector or stretching the vector should go like delta squared. I'm just making a rough model with what we know about fuzzballs to model how the thing should behave. And also, it shouldn't be like a spring, like I can keep stretching and stretching, getting an arbitrary energy out of it, or keep compressing and compressing, get an arbitrary amount of energy out of it, because it's just a bound state like a positronium. If you stretch a bound state too much, it just breaks, and then there is no more energy increase. So you can only stretch or compress it up to a factor of order 1. So if you take delta C to be some number of order 1, I make it look like delta squared for small delta, but when delta becomes order 1, okay, the energy doesn't increase anymore. So I'm just making a schematic model of something which is compression resistant, but you can't get infinite energy by compressing it. At some point, there's no fuzzball configuration. We're back to just local vibrations in the vacuum. We also need to set the scale K of this energy of the deformation. And to set the K, we'll just use the words we've been saying before. If you do an order unity deformation of the vector, you take a vector of radius r, increase it, let's say, to radius r by 2, the energy increase should be of the order of a black hole of radius r. Okay, so that's the kind of scales we are putting in from what we know about on-shell generic states, which I was saying, but I'll just assume that for these virtual fluctuations as well. Well, that's the energy scale in d space dimensions. That sets this value k. And so then we can use this as the rough expression of how the vectors, the energy changes when you compress them. Again, we have put nothing more than our intuition. So there's nothing correct about this expression. It just mirrors the fact that the vectors are local minimum of the energy. Energy increases quadratically when you around the minimum. So you don't want to stretch or compress it if you don't want to increase the energy. And again, these delta C and beta are numbers of order 1. And this just sets the scale, same scales we've been talking about. Okay, so we won't need this modeling in detail. I just want you to say that, okay, we have now something concrete at the back of our minds. At least there's a picture. And now let's use that picture to solve the 3 puzzles that we had. Let's begin with the information paradox. So here's a semi-classical picture again. If you take a shell which is collapsing, time here is going upwards. The shell comes closer to its horizon radius. At some point, it becomes equal to the horizon and goes inside the horizon radius in the classical picture. But once the shell is inside the horizon, then between the shell and the horizon, the light cones turn inwards. So no data can get out. So then this horizon persists here. You get the entangled pairs and you get the information puzzle. But let's see what's going to change in this picture. So again, I just draw the shell out here again. And here the shell has gone inside the horizon. And now what I'm going to ask is at each of these steps, let's ask also what happens to the vector part of the distribution function. Now, let's take the shell to be coming in at the speed of light. So inside the shell radius, the information hasn't even reached that the shell is coming. So by causality, that part of the space, the vector distribution hasn't changed. So that's not the part I'm worried about. But let's look at the vectors which are outside the shell. Now, as we said, those vectors see the directional pull of the shell. And so they are getting compressed and they are getting squeezed. And let's see what happens to them. Now, if you put any object, let's say a star in some space, it squeezes all the vectors around it. That's the kind of picture we had when we had a shell. All the vectors of radius bigger than the shell, well, they feel a potential and those vectors get squeezed a little bit. The energy goes up a little bit. You have a schematic modeling for how much energy goes up and so on. But if you have a star, the vectors just compress a little bit and then they stabilize because they are compression resistant. Now, there's something different when you actually make a horizon. Because now you look at the vectors out here may just compress a little bit and then just stabilize. But if you're inside the horizon, see what happens. Inside the horizon, the light cones point inwards. And virtual objects actually follow the same rules of causality as real objects. So in fact, once you're inside the horizon, if you look at a vector whose radius is larger than the shell, but still inside the horizon, it has no choice but to keep compressing. So this vector cannot stabilize, and that's the crucial point. Once you form a horizon, the light cones are such that this vector configuration keeps compressing. And at some point, the energy of the vector goes up by this scale, which we had seen. And in fact, the vector structure is completely destroyed. And this is then the picture that we get for what should happen. This is the classical picture, traditional picture. The star just comes, becomes a ball, and then this makes a singularity, goes there. But now we are saying let's also follow the vector part of the wave functional. So the vectors out here they are forced to compress, and then they actually turn into on-shell fuzzball states, and you just end up in a time of order crossing time with just a fuzzball, that's when all the new effects come and the vector structure is completely destroyed. So if you want to see that in terms of the potential energy graphs that we were drawing, so now we've drawn the graphs a little better because, as we go through our building our picture more concretely, we also try to improve our pictures. So this is the semi-classical part of the wave function. Then you can have vectors of small radius, they have some energy, because larger radius have even larger energy. So the actual graphs of vector graph is not just like a square box, it goes up towards higher and higher vectors. You should draw it like that. And there's the spread of the wave functional in these graphs. So that'd be the vacuum wave functional. And now when you actually put a heavy object inside, so there's a compression on the vectors, then a vector of large radius, its energy goes up a lot because the vector wants to compress, it wants to fall in strongly in the gravitational potential. We still want to hold it up at that large radius. Well, it has a lot of extra energy. So this height of this barrier is now huge. The wave function no longer actually leaks in there because the barrier became very huge. The wave function dies very rapidly before going in there. But now it becomes oscillatory over this region where you have these smaller fuzzballs, and that's this fuzzball formation. So I'm not spending much time in doing this because I guess all I'm going to give you is a picture, but all the various potentials we have drawn, the various scales for those potentials we have drawn, and the rough qualitative picture about how these vector fluctuations just become on shell when you crush them beyond a certain point. All the various things we have put together sort of give you this picture that, as we said, when you crush these guys in, the virtual fuzzballs you had actually just become on-shell fuzzballs. And what is crucial about the horizon scale here is that if you're outside the horizon scale, the vector could just compress a little bit and just stabilize, like what happened to the star. As it comes closer to the horizon, the compression becomes more and more. It's more difficult to stabilize, but still they can. But once you're inside the horizon, because the structure of the light cones, you must keep compressing, and then the thing actually, the wave just spreads over the on-shell fuzzballs, and you actually get fuzzball formation. So that's how one would argue in this picture that you deviate from the semi-classical expectation. Okay, let's go to our second puzzle, the bags of gold puzzle, or the puzzle of unbounded entropy. It's a very beautiful puzzle, but not everybody may have thought about it. So let me take a minute to just state the puzzle in some detail first. And the puzzle basically is the Beckstein entropy a counter states? So we know the Beckstein entropy is like A over 4G. That's an answer we can get easily from classical gravity. Does that correspond to this many actual states for the black hole? And one might even conjecture the black hole has a maximal entropy. So with energy m in a region of radius r equals to gm, somehow you should not be able to hold more than e to the s Beck states. But actually the puzzle is that if the semi-classical picture of the hole is correct, then you can put an arbitrary large number of states inside the horizon radius and with an energy which is still equal to m. And so what is that construction? So take the Schwarzschild hole, that's the metric. And the crucial point about this metric, of course, is that for r bigger than 2m, a space-like surface is like t equal to constant. And for r less than 2m, a space-like surface would be something like r equal to constant. So if you take a region like r equals m, that slice inside the horizon, so it's not near the singularity, not near the horizon, just something nicely in between, then it's inside the horizon, but it can be arbitrarily long. So here's the black hole picture drawn in Eddington-Finkelstein coordinates. Here's a shell which collapses to make a black hole. This is a classical black hole picture. And then there's a singularity at r equal to 0. But if you want to draw space-like slices in this geometry, here's a space-like slice which is t equal to constant near infinity. But then inside the horizon, you can smoothly join it to an r equal to constant region. And then you can make this region as long as you like. In some sense, all the difficulties with black holes actually come from this fact. And then here you can smoothly close it up. And so it's a complete smooth space-like slice. But on the slice, as you can see, we can hold an infinite amount of data. So let's say this black hole had radius 3 kilometers. I'll put on this slice scalar field quanta of wavelength 1 kilometer. And even space them apart widely, let's say 2 kilometers apart. So everything is very low energy there, but the slice is very long. What's the energy of any of these quanta? Well, the local energy is just positive given by the wavelength inverse, but the energy as seen from infinity, which is what will tell me the entire mass of this object as seen from outside, is given by taking the killing vector for this space-time and dotting it with the 4 momentum of the photon. And so if this photon is one of these red ones pointing this way, when you do this, you find energy which is positive, but it's pointing this way, you find energy which is negative. These are just the negative energy quanta which are produced in Hawking radiation. Inside the horizon, you can have negative energy quanta. I just drawn them out more explicitly here and just written how much negative energy they should have. But now you can see from this, it gets to an arbitrary amount of entropy inside the horizon, with the total energy still being m, because these energies you can make them cancel. The energy m comes just from this shell which we have on the slice. If each of these photons had, let's say, 1 bit of entropy, you can store an arbitrary amount of entropy in the whole with an energy budget just E equals m. So that's the puzzle. So then is A equal to 4G really a count of states which you can put in the whole? You might try various things. You might try to make some reason that very long space-like slices are not allowed, because to beat this bound, slice must be very long. But there are severe difficulties with that approach. You can discuss that offline if people are interested. And actually, this bags of gold problem is stable against all sources of small corrections. You might say there is a small correction that can do this. Maybe there's this small effect I've forgotten, this tunneling which I've forgotten. But I've tried to argue in this paper that actually using an extension of small correction theorem, you can actually prove this problem is completely rigorous as the information paradox with the small correction problem. So as long as your physics is all, has this no very non-local effect like the wormholes and so on, this is a problem which you can make rigorous. Okay, so is there a solution to this puzzle?
I have.
Yeah, go ahead.
Sorry, maybe there's somebody else, but okay. My question is one that these excitations are slightly unusual in that in some finite proper time they all tend to collapse into the singularity. So they're not quite like stable excitations we think about in in a gas in our room, which are arbitrarily long-lived. That's because after some time, because everything collapses into the singularity, these excitations will also do that. So I just wanted to check. Would you agree with that?
Yes, of course, but that's not a problem for this bags of gold problem, because what happens is if you take this particular slice, and now this is the space direction, right? And if you look at the future time direction, that's the radially inward direction, right? And so what you get here is just like a cosmology. So this is like a slice for cosmology. It is heading towards a big crunch. Actually, you can mathematically map it to exactly that, right? So it's just like saying if I have a big cosmology today and I have low density matter in the cosmology, and let's say it is heading to a big crunch, it's just a time reverse of our Big Bang. So there's nothing worse about these quanta on this slice than the photons we see around us today in our universe, because just when t going to minus t, the Big Bang we got is exactly this big crunch. So yes, the big crunch will come in some time, just like the Big Bang was at some time, but that's all that is. There's nothing wrong with them per se. The entropy on the slice is still what it is.
Right. The second thing is that in counting the entropy, I think you're assuming that the inner product between two widely spaced excitations goes off exactly to 0, and you're not willing to allow an e to the minus s kind of tail in the inner product between two excitations if they're widely separated. Is that correct?
Good point. So in fact, I am willing to allow that. So you can put small correction. That's what I meant by saying stable against small corrections. So if you make small corrections saying, okay, you take two quanta which are very far and they can have this little bit of change in the energy which I put between them. And so there's a slight increase in energy between one guy and maybe one more guy somewhere. The point is you can take that into account by making, let's say, the negative energy quanta be slightly shorter in wavelength than the positive energy quanta. And then you can just offset that energy decrease again. Then you may say, I have too many quanta, and each quanta can talk to any other one. And then there are some other issues you can deal with that, in the sense you have to ask at any given point on the slice, what are the degrees of freedom which are telling you how big the rest of the slice is. So we should actually talk about that perhaps in detail at some point, because there are actually many models you can make if you allow sufficiently big non-local effects that take you, let's say, with wormholes connecting you far outside or things like that. Then there are ways to bypass the puzzle. So as I had said, since I'm not allowing those things myself at the moment explicitly, I don't have recourse to those ways of solving the problem. But yes, allowing those kinds of long distance non-local effects, there are other ways to get around the puzzle. So I'm just sort of ruling them out by fiat at this point. But in terms of all the physics which I have allowed myself, that I have causality and local physics, so on, small energy changes actually can be taken into account, and then that's the kind of small correction arguments we have to make in this paper. But maybe we can talk about that during the discussion.
I would like to mention another possible resolution of the puzzle. Well, what I believe is the correct resolution. Okay. Could you go to the next transparency? So the formula on the top is telling us what the entropy of the black hole is from the outside. Okay. Yes. And the puzzle arises from thinking that it should capture the entropy of all the matter that is inside, right? The entropy of the matter inside seems bigger.
Yes.
Okay. So the current, this work on islands and the page curve and so on from last year What it suggested, what it showed, I think, is that this entropy is, and what it showed is that the degrees of freedom that describe the black hole from the outside do not describe the whole interior in this case. They describe only the part of the interior that is outside the Rutakanagi surface, or the quantum Rutakanagi surface, which in this situation that you are discussing would not be the whole interior of the black hole. It would be relatively close to the horizon.
Yes.
And so, so then there is no puzzle. So the quantum degrees of freedom, whose number is what was the formula in the top of your the transparency that was there before, is counting just those degrees of freedom. I mean, it's covering only up to the RT surface. Whatever is beyond the RT surface, well, it's, or the quantum extremal surface, maybe I should say more precisely.
Yes.
What is beyond that is described by other degrees of freedom that depend on what that matter that is inside is entangled with, but not by the number of degrees of freedom of the black hole itself.
I understand. Actually, I've spent quite some time trying to read your papers. And in fact, in one of my sort of extra slides, which I wasn't going to cover in the talk, I think I've tried to draw a picture of what I understood from your papers. And I think this is also what you're saying. This is the black hole horizon. Some of the quanta inside are really not part of what you would like to capture inside the black hole.
Yeah, exactly.
Really connected with infinity. This was my picture, what I understood from your papers. And yes, so as I said in the beginning, I'm explicitly not considering these kind of models where things which are inside the horizon radius are really bits which belong far outside and so on. But that is a completely different or maybe self-consistent way of thinking. And since we didn't allow that from the beginning, that's why I didn't show that up there. So that's agreed. So yeah, with an assumption of locality, then I don't have that option. And so that's not here right now. So we're just trying to solve this with the fuzzball paradigm, but everything is local. The fuzzball is just the actual explicit constructions we find, whose examples we have found in string theory. Once you've found some fuzzball fluctuation, of course, you can have it in virtual fluctuations, and then just using that and no other black hole not doing anything special for me, I have to solve all my quantum gravity puzzles. So in that sense, I don't actually have these new tools of the non-local thing, which I will not myself.
Samir, we're coming up on the hour. I don't know what time scale you were planning on finishing on, but I would also like to hear about the cosmological part of the story. So how much longer do you think you need at this point?
So can I have 10 minutes?
Oh, certainly. 10 is no problem.
Okay, good.
Right.
Yeah, we're almost there. So, so let's see if we can have a solution to this puzzle in the limit setup that we have. We just have fuzzballs. We don't have any non-local effects or something which are allowed to us. So again, we have to ask, what is the Vecro part of the wave functional doing in all this? We've just done the semi-classical geometry, but there are Vecro fluctuations everywhere. And so we should also see what the Vecro part of the wave functional is doing. So again, in flat space, you could consider a Vecro of radius RV prime, and that's the outer radius in flat space like this. But then as we said, if we deform the space, we bend it, let's say to the kind of slice we get in the bags of gold construction, then for the same outer radius of the Vecro, the actual length of the Vecro has become more. The radius thing has been stretched, and that costs me an extra energy. So if I do the stretching of the slice by the same order, let's say, as the black hole radius, if I even make it, if the black hole is 3 kilometers in radius, if I stretch the vertical part of the cylinder I had drawn to, let's say, just of the order of 3 kilometers, the energy of the Vecro configuration actually goes up by order m. And so on this particular space-like slice I had drawn, I find I not only have the energy m, which came from the shell, which made the black hole. Of course, I have that on my slice, but I also have an extra energy from the stretching of the Vecros, which is also of order m. And so the total energy on the slice becomes more than m. So in fact, that slice doesn't fit in the black hole geometry, which only has mass m from outside. So what we actually find is that in classical gravity, we free draw ourselves all kinds of slices and say, all these slices with the same asymptotic m are all allowed because inside, they can have any shape. But then when you start taking the Vecro part of the wave functional into account, you find that's not quite the case. And some slices actually have an energy which sharply goes up. And if you look at the bags of gold slice, it just doesn't have mass m. So when you try to write this Wheeler-DeWitt wave functional, it doesn't actually spread over this slice. This part of the slice is deeply under the barrier. So in fact, that takes away the puzzle in terms of the potential energy diagrams. What has happened is that the energy of this Vecro is now sharply more than it had in the flat space case. So this barrier height has now gone up. The wave function now cannot leak much in there. the wave function therefore gets compressed, the energy of the wave function goes up, and there you no longer can fit that slice in the geometry. So the Wheeler-DeWitt wave functional, that's what it's talking about. If you write that for the entire situation, is different from what you would expect to have expressed classically, and sharply different in the region where it would have had support in these long bags of gold slices. So it's not like the slice can be as long as required to hold the Bracketsian entropy. Once you just make it as long as the horizon radius and so on, the energy already starts increasing over m. So you don't actually get those slices. Okay, let me just take 5 minutes to talk about the cosmology, and then I will end. So take a flat dust cosmology. So there is the metric, and just an expanding cosmology. So you have a dense matter, and then just dilutes, and you keep expanding. Okay, so I'll actually focus, in this homogeneous infinite cosmology, I will focus on a small ball-shaped region, which is given by these dotted lines, and we just focus our attention on that region. Now, suppose you give me two things. CPT invariance, which normally most people are happy to accept for, let's say, string theory. And we'll assume that the Birkhoff theorem holds to leading order when we have gently curved spacetime. Also something that most people are happy to agree to. Then we'll see that the black hole puzzle information paradox can be actually mapped to a corresponding problem in cosmology. I can map the cosmology to a problem with the black hole. So the expanding cosmology, again, has anti-trapped surfaces. If I draw a surface big enough, then the light cones point purely outwards. And again, by time reversal, just to CPT, you can map the expanding cosmology to a contracting one. And then it really looks like the black hole, which has trapped surfaces. But of course, the only difference is a black hole has some dust ball, but asymptotically empty space outside, while the cosmology has dust going on and on. So a priori, they look like two different situations. But we'll actually map them one onto the other. So how do we do this? Even for this classical gravity, for a dust ball, you know that the way the dust ball collapses, the interior of the dust ball, it doesn't actually depend on the presence of the dust outside that ball. And that's just by the Birkhoff theorem. In a spherically symmetric situation, you can throw away the outside, and how the inside evolves doesn't care about the outside. So let's go ahead and do that. Even though our cosmology has also dust outside the ball we are focusing on, we can throw it away and replace it by flat space, and then the evolution of this dust ball shouldn't change. Well, that's for classical gravity, but let's assume as long as we are gently curved space and all densities are low, that some version of the Birkhoff theorem, up to small corrections, holds also for our full quantum gravity theory. So that would at first appear reasonable. But suppose we do that, and let's keep focusing on then this ball-shaped region in cosmology, when the outside we have now argued we can replace by flat space. But now we seem to have a puzzle. Let's ask, will this ball pass smoothly through its horizon radius as it goes in? Well, if it doesn't, then we have if it does smoothly pass through its horizon radius, we have a problem with solving the black hole puzzle. Not just with the fuzzball way of doing it, but any method which says that something happens at the horizon, then whatever theory that is that somebody has cooked up to solve the puzzle, it says that when this particular ball of dust approaches the horizon, something must happen. But then if you look in the sky and look at a region which has the size of the ball of dust, we said by the Birkhoff theorem, it doesn't matter that there is dust outside, we can replace it by flat space, then it does look like the black hole puzzle. And then let's ask in the cosmology, does something happen to a ball of dust as it crosses horizon radius? And the answer is no. We can actually look in the sky, and we can look at, if this is today and this is us here, we can look in the past, and the past we can see up to the particle horizon. I just restricted the time when we had dust onwards. So at that time, the particle horizon, let's say, is this big. And with that mass we see in the sky, the horizon radius of that is actually much bigger. The Schwarzschild radius of that is much bigger by a factor of 10 to the 4 than the actual ball we see. So we can actually look in the sky and see that there are balls of dust which are compressed to a radius much smaller than their horizon radius, and that no novel quantum gravity effects seem to be taking place there. It just looks like semi-classical physics over there. So any theory which tries to say that something new happens when something is crushed beyond the horizon radius, how do they square with what we see in the sky? But this puzzle has a natural resolution under the Vector hypothesis. In fact, the cosmological situation cannot be mapped to the black hole situation. And the reason is the following. We not only have to look at the dust which we see semi-classically, we must also ask what are the vector fluctuations doing. So in the black hole, you remember that once we form a horizon, the vectors inside the horizon have to keep compressing and compressing, and then they just get destroyed in order the crossing time. The bound states just break, and there are no vector configuration, with just the local bubbling of the vacuum. So When you go to the cosmology, instead of the trapped surfaces, you have these anti-trapped surfaces. And by the same logic, if you look at a vector whose radius is larger than the cosmological horizon radius, it gets stretched and just breaks apart. It can't stabilize by its compression resistance because it just keeps stretching and stretching. It just has to break because it can't stabilize at any radius because of the structure of light cones. So in the cosmology, the vector fluctuations can have a radius which all the way from 0 only up to the upper radius. We don't have vector fluctuations of all sizes. So here's the difference between flat space and the cosmological situation. Flat space has vector fluctuations of all radii from 0 to infinity, while in the cosmology, the vector fluctuations end at the Hubble radius. And so, in fact, you cannot really use the Birkhoff theorem to throw away the outside of the dust ball that you are focusing on and say, I can map it to the black hole puzzle. Because otherwise, we indeed did have a serious conflict with any puzzle that tries to solve the black hole problem by saying that something novel happens when the black hole reaches the short radius or smaller. Okay, so in solving this cosmological puzzle, we have learned that we should now have a new ingredient in the way we think about quantum gravity, which is what I call the vector distribution function. So here on the x-axis, I plotted the vector radius RV. And in flat space, we just have vectors of all radii. So I can just draw that by a flat line. But in cosmology, so the vector distribution ends at when the vector size, the vector configurations here, when the vectors reach order the Hubble radius, it just dies. So you can't actually understand what is happening to any given situation unless you talk about what's happening to the vectors there. I had a couple of slides about bubble nucleation. Let me skip them and come back to it in the question session because I just want to put one slide for the summary and end. So when are vector effects significant? What the effects we are talking about? So as we have said before, take a space which is curved. This is just a depiction of curved space. And suppose the curvature is at a radius, curvature radius RC. And suppose the radius over which the curvature persists, let's call that L. Suppose L is much less than RC. So what does this mean? Suppose you take a star. That's in this situation. A star, let's say, has some radius L, but then it's very gently curved because it's not very massive. It's very gently curved. So the curvature radius RC is much bigger than L. In those situations, there's no severe distortion from the vector component. There's just some tail of the wave function distorts a little bit because of the star. Those effects are included in the semi-classical gravity, and there's nothing more to say about it. Where do the new vector effects come? So whatever the curvature radius RC you had, suppose that curvature persists for a distance L, which is comparable to or bigger than RC. And that's when the vectors start getting squeezed by order 1, and that squeezing generates an energy increase of this order, and then the vectors can become on-shell, and all the new physics starts. And so this happens whenever you reach a black hole horizon or a cosmological horizon, and you can then see that this kind of effect, which distinguishes this from this, cannot be actually captured by a simple change in the local Lagrangian. Like the Einstein-Lagrangian Ricci scalar, you can add to it R square, R cube terms, but then the C1, C2 are order Planck length or string length. So these new terms become important when you reach the Planck length or string length, some particular length scale. But that's not what is happening here. You can have any curvature radius whatsoever, could be a mile. The only question that where the vectors become important is whether the distance over which the curvature radius persists, is it just 10 meters or is it a mile or more? If the curvature radius is anything, even a very long curvature radius, but persists for a distance which is also of that order, the vector effects take over and you get novel physics. And so that's why we can't actually capture them with the local Lagrangians. And so then that's here my last slide. As I had said, we should ask whether all the different horizons are similar. In classical gravity, they sort of look similar. The Rindler, the black hole, the cosmological horizons, but I would argue they're not similar in quantum gravity. So in Rindler space, this horizon just arises from a coordinate choice in Minkowski space. And so the energy everywhere is just zero. It's just empty Minkowski space with energy 0. There are no on-shell fuzzball excitations anywhere. And the vectors exist over this entire radius 0 to infinity. Now the black hole looks like Rindler space near the horizon for the classical black hole, but actually you get that in the opposite limit, m going to infinity. The Rindler space was for m equal to 0, but now you have m go to infinity to get this. The interior of the horizon is now filled with on-shell fuzzballs, so the horizon is not a vacuum region. But of course, you have the normal vector fluctuations from the horizon radius outside all the way to infinity. And the cosmology is the third thing. Now there are no on-shell fuzzballs here, so that way it's a little bit more like Rindler. But the vector distribution doesn't go all the way to infinity. It actually ends at the horizon radius, at the cosmological horizon radius, Hubble radius. So at the Hubble radius. So in fact, to solve all the various paradoxes we get from black holes and cosmology, we must take into account this virtual fluctuations and the vector distribution function. And this is actually sharply different in different cases. And then once we take it into account, I believe that all the different pieces of the jigsaw puzzle we've been having with quantum gravity over the years, I think all the puzzles neatly sort of fall into place and we get a picture which is consistent overall. Okay, so I'll stop there. Thank you.
Okay, thank you. Thank you. Questions? Comments?
Yes, please.
So I had a question about the cosmological puzzle. So do I understand correctly that you have a puzzle only if you accept the Velcro hypothesis? Or is there some other puzzle? I mean, in the case of black holes and so on, there are well-known puzzles which, like the Hawking information paradox, the bags of gold, that I understand what they are independently of any hypothesis on how to solve them. What is is there a puzzle in cosmology that you are talking about that you want to solve that does not rely on any particular method of solution?
Yes. So actually the puzzle has nothing to do with the vectors. The vectors actually allow us to get out of the puzzle, but the puzzle is there regardless. So let's just say what the puzzle is. Okay. And the puzzle is that you can map the cosmological situation if you take these two assumptions, that the Birkhoff theorem holds leading order in gently curved space and you have CPT invariance. You can actually map what you see in the sky exactly to the information paradox. So we're just mapping the cosmological situation to the information puzzle. And then it's the full power of the information puzzle, because then if you use a small correction theorem and so on, you can then make it completely rigorous. So I'm arguing there's actually a rigorous puzzle there, which I haven't tried to make it sort of rigorous here, but I'm arguing it's completely rigorous. And the way we did that is we said, just focus on one ball-shaped region in the cosmology, which is, by time and ways, you can think of it as shrinking rather than expanding. And then if you just look at this ball-shaped region by the Birkhoff theorem, it shouldn't matter what's happening outside. And then it's exactly like a black hole, which is actually shrinking. And so any theory which tries to solve the black hole puzzle by saying that something happens to the black hole, doesn't even have to do with fuzzballs and certainly nothing to do with the vectors. Anything which has to do, say, any theory which comes and says something new happens when a ball of dust passes through its horizon radius and becomes, let's say, 1/10 of its horizon radius. Suppose someone says, I think the following new physics happens. Well, you look up in the sky and you can see balls of dust.
I understand that it's a problem with this kind of solutions, but there are other solutions to the black hole problems that do not involve this hypothesis. So then this puzzle does not arise for those other solutions.
Absolutely. So if somebody has a solution where, for example, you have these non-local effects that you use to identify bits near infinity inside,
then we don't have any.
You will have to find similar solutions to this puzzle there also.
Well, I don't know what this puzzle is. I haven't understood this puzzle. This is only a puzzle if you assume that something new happens. So if I don't say something new happens, then I don't see what the puzzle is.
Agreed. But something new has to happen to solve the black hole information paradox. And so whatever you did to solve that puzzle,
I don't agree with that.
Okay.
Because the recent progress showed that nothing new has to happen. Nothing new in the sense of a change in the geometry. I mean, there is a change in the assignment of the fundamental degrees of freedom that we used to describe the geometry. And for black holes, there is a more or less clear statement of what those degrees of freedom are, or the degrees of freedom of the black hole as seen from the outside and so on. Yes. But for cosmology, I don't know a similar statement. So that's why I don't understand what the puzzle is.
Good. So I understand what you're saying. If there's no change in the semi-classical picture that you need for the black hole, but just the degrees of freedom are to be identified or counted in a different way, then yes, you don't have anything to do right here, except that you have to then go and say, in the cosmological situation, you can explore what is that new identification of degrees of freedom you need in the cosmological setting. And so that's still a question for you in your model. And you don't actually face any sharp puzzle because nothing new is happening when the ball is squeezing past its horizon radius. So I agree with that. But then you should still ask about what the identification of degrees of freedom that happens between the degrees of freedom inside the cosmological horizon and outside. Perhaps that's still a question for you then, right?
Okay, thank you.
So, sorry, could I just add a comment to that?
Yes.
I just want to emphasize once more that this idea that the degrees of freedom inside the black hole are the same as the ones outside. This is not a postulate of new physics that occurs only in the presence of a black hole. In fact, you would expect that a similar effect, for instance, exists even in empty space. So the idea is that if you take a very complicated combination of observables on a sphere very far away, you can use that to write a degree of freedom somewhere in the middle of the sphere. So this idea of complementarity is not unique to black holes, and this is something, and this is actually not even a postulate of new physics. if you just take semi-classical gravity and just follow it to its logical conclusion, even in a situation like the vacuum of global ADS, where you think you understand everything, you could derive that such a relation has to exist between degrees of freedom. So I just want to emphasize that these other resolutions are not postulates of some new physics. They're just using standard physics that we understand well and just following it to its logical conclusion,
Okay.
including, as I said, in the vacuum of ADS.
So I have not, I tried to study those papers, and I must say that I have not agreed with the physics there, but maybe I can just ask you a question about that. So if you make the black hole there, maybe at this point I'm just asking you for the difference in what your picture would give you. You would still then have, if you just look for the creation of just one or two entangled pairs around the horizon and the full, fine-grained picture, you really would have a vacuum around the horizon, and you still get entangled pairs like this. If you don't actually make some non-local identification of degrees of freedom, then I think you can't get around the black hole puzzle. But I think you are thinking of some that the degrees of freedom in gravity are a little bit non-locally entangled or defined. And so somehow when the black hole radiates, the degrees of freedom are not completely local and like sitting in your hand the way you would think in normal flat space physics when you burn a piece of paper. I'm just trying to repeat what I think the picture that maybe you or Juan are saying. I'm not saying I understand the picture, but it is indeed different from the puzzle picture that I was using here. And so I agree that all those three puzzles we have, you should go and
maybe just to clarify, I think that everyone would agree that if you look at the ultimate UV description of the degrees of freedom, the true description, it is not in terms of these entangled pairs that you have on this slide. So the true wave function is not these entangled pairs raised to the power n. The true wave function is something different, which is described in terms of some holographic degrees of freedom. And the point is just that there is an effective description of the physics in terms of entangled pairs that is accurate if you make a small number of observations. But the true description is very different. But I think that is something that we see often, that the true description of the gas in this room might be in a pure state, but effectively it looks like a thermal state.
Very good. So in fact, what I tried to do was I tried to make a bit model of the kind of things that I've been reading in yours and Juan's and other papers on this. And I found the following, which let me share with you. It's not something I have written up or anything, but we can discuss it certainly. So exactly as you say, let's say that the actual full quantum gravity wave functional, I still have to ask what the full theory is doing. If I first take some approximate theory, then I maybe can't address the Hawking puzzle. In the full theory, at least when I produce one or two pairs around the horizon, I should see for a short time of the order of crossing time, physics like the physics of the room, and I will see the entangled pairs being created. But perhaps when you have many pairs, you can do something delicate between them, some things you can do differently to define your bits, and then maybe you can resolve the puzzle that way. So I tried to make a bit model of what you are saying, and at least when I try to do that, I can actually make sharp statements about how a radiated bit from the black hole would behave when you capture it very far from the black hole. Suppose gone far out of the black hole distance m cubed, and suppose I capture it and I try to say, will this behave differently from the way I thought a bit should behave, which it just came out of a radiation of a photon from a piece of burning paper. And I actually find that there are differences. Now, I could be wrong in my bit modeling, but I would love to see if you make an explicit bit model of what happens when the bits come out, what happens when the black hole is gone. If I could actually see a toy model of what is happening to different degrees of freedom, maybe I would understand better, but I would certainly be happy to share with you my bit models. And I'm not saying they're like wrong, they necessarily say that what you're saying is wrong, but they actually do say that if I take a bit which is far away out of the black hole and I pass it to a Stern-like experiment to measure something, it behaves differently from what I would have done if I had normal piece of burning coal. So whether you agree with that or not, maybe we should have a good discussion about it, perhaps in the discussion session.
Yeah, sure. We should have a longer discussion. Let me just say one thing. In the when we describe this construction of the interior, we did have these bit models. So there, the ultimate description is just in terms of the degrees of freedom that live outside. It's just in terms of n qubits. But there is an effective description that seems to double the degrees of freedom. And you can explicitly, write down what that effective description is. And you can also see when it breaks down. It breaks down when you start making a very, very accurate experiment. So I agree with you that the ultimate description cannot be in terms of these two n degrees of freedom, one going out and one going inside. but the effective description can still be of that form. But as you say, maybe we can discuss this
Yeah,
later.
absolutely. We should just make an explicit bit model where somehow the effective one comes out like this and the actual one is something else. And we just see what it actually gives in terms of observations.
Yeah,
so
I
it
just
doesn't have
want
to be the
mention,
correct physics, but let's make a model like that. I think that would be very nice to see.
Okay, so are there any other questions or any other comments?
Just a general comment is that it's hard to believe the classical geometry doesn't have more validity than you're allowing for. For example, there's the traversable wormhole story of Gal, Jafferis, and Wall, which seems to match nicely with manipulations in the dual boundary. And it seems hard to reproduce if the classical geometry behind the horizon isn't correct. That's just one example.
Okay, maybe I should look at the result you mentioned. I'm not that familiar with the traversable wormhole paper you mentioned, but let me ask you, what is your picture of classical? The reason we are arguing against the classical black hole geometry is because the information paradox can be made stiff and rigorous, and it's difficult to get out of it without a non-local identification of bits of the kind that we were just talking about. Do you also have in mind that there's a non-local identification of degrees of freedom in this than what you would expect from just a normal local physics? And you would need to keep that in your picture of the classical black hole?
I don't have a solution of the puzzles to offer, so I can't answer. But my only comment is that there's a lot more success at extracting physics from the classical geometry than seems plausible to me if your picture would be the whole story.
So there's one part of this picture which I didn't talk about because somehow it was not relevant to the three paradoxes I was talking about. And that is the picture that if you actually are looking at excitations of a fuzzball, is the picture, the story of fuzzball complementarity. If you're looking at excitations of a fuzzball with under impact of infalling objects with energy bigger than the temperature, E much bigger than T, then it's still possible. In fact, I made a bit model to show how this might work. We don't know if it is true, but it's possible to make a bit model to say that it can reproduce the semi-classical physics of infall for this object over times of order the crossing scale. But as E starts approaching T, the approximation breaks down, and it's only valid for infalling objects and doesn't describe the outgoing negative energy quanta which are inside the horizon, which are these partners C of the entangled pairs. So if you actually say you want a local region around the horizon, let's say of a 3-kilometer black hole of radius 1 meter for that region, I'm going to ask you, is the quantum state in that region close to the vacuum state up to corrections of order epsilon? Correct? If I take a dot product of the state psi with the local vacuum, is it close to 1? And if it is, I think you need something very new to get out of the black hole puzzle. With the first one, I'm saying it's not, but then, so that's what resolves the Hawking puzzle. But still, when you probe this object with infalling objects of E much bigger than T, you can still extract some effective dynamics of vibrations of the fuzzball, which can mimic classical dynamics. But I don't know whether that can actually give you the traversable wormhole part of the physics you're looking for. And so that I will have to see.
Okay, thank you.
I think the transversable wormhole is actually non-local because it has it's a global ADS which has two boundaries. So basically, there are two boundaries which talk to each other. That's how we get the transversable wormhole. So I think it's intrinsically non-local. That's the question which Samir was asking.
Good. Yeah. Let me say something about the thing you just said. So a lot of the things that Juan has developed and so on starts with the eternal black hole picture, which is just the Einstein-Rosen bridge, and it does have two sides. And we start with that picture. It looks somewhat compelling that since you have two boundaries, there should be an entanglement leading to these kinds of wormholes. But on the other hand, in the fuzzball picture, I would argue, it's a paper I wrote some 5 or 6 years ago, that in fact the eternal black hole geometry doesn't exist. If you try to make that geometry, and if you look at the vector of fluctuation on that geometry, that's the kind of slice that's the bag of gold slice, and the actual energy of that configuration is more than m. So in fact, the Einstein-Rosen bridge, for the same reason that the bags of gold geometry can't be actually fitted in a space-time with the asymptotic mass m, the double-sided black hole, which has the Einstein-Rosen bridge, the Einstein-Rosen bridge geometry also cannot be taken as an initial condition to evolve the geometry further out and behind into the space-time. So that is where so very early on, the picture that Juan has and the picture with fuzzballs seems to deviate because the starting point of that, the eternal black hole itself is very close to the bags of gold slice, and that slice already doesn't exist. If it does, what can again lead to exactly these kinds of puzzles, which I tried to make rigorous in this paper from 2014.
When you say that they don't exist, you think they don't exist, or what is that statement? I mean, because they do exist. I mean, it exists as a configuration, and something similar to a bag of gold forms when you have the process of Hawking radiation, because you, at very late times after the page time, you have a black hole interior which has more entropy inside than the Bekenstein entropy of the black hole. So.
Right. So what I would argue is if you try to make that classical geometry, which is of the shape of the Einstein-Rosen bridge, at first in the classical physics and just with semi-classical fluctuations, it looks, okay, I can have this completely smooth initial condition. But actually, once you look at all the fluctuations of these virtual black hole states, you find, no, actually they distort the wave function, lead to an effective energy increase, which makes the total energy more than m. So in fact, that slice cannot be fitted as an initial condition for once you take all these vector fluctuations into account, it cannot be fitted in asymptotic geometry with mass m. Now, of course, you may say that's the postulate. Maybe I don't have the vector fluctuations, or they don't do.
Yeah, I would say that, yes.
Right. But then what I showed in that paper was you then face all these puzzles with like the bag gold puzzle and so on, to which then you have to find solutions with the kind of non-local identification of bits which you are talking about.
So that's my favorite solution to those puzzles. So I don't bother.
Yes. But if you take that solution, then we should really talk about the bit model, which I tried to make to understand what you have done. And what I got from those bit models was that the physics behaved in ways which I found unacceptable. And I would love to have that discussion with you. With those
well, a bit model for the traversable wormholes and so on is the SYK model. And in the SYK models, you have configurations which behave very similar to the wormholes and traversable wormholes and so on.
Yeah, actually, I would like to see a bit model of what would happen when these entangled pairs are created, the guys which go inside, how they somehow become bits which are not really now sitting in there, but somehow become identified with bits outside. When I do that, I find there are energy costs to that, which make the bits at infinity now no longer have the same behavior. When you examine them, they are different from the bits which you would get by burning a piece of paper, which are not really somehow having an image which is somewhere else. So if I'm wrong about that modeling, I would love to understand.
Okay, I guess I don't know your model, so I can't say anything.
Yeah.
We'll have a discussion in, I think, both tomorrow and the day after. And I think there'll be plenty of chance to continue this.
Yeah. Any other brief comments? We should wrap it up, and it's going to start again about almost 12 minutes or so. Okay, so we'll start panel discussion 5:45 and pick up from there. Thank you, and thanks, Samir.
Thank you.